Okay, perfect. So, hi everyone, my name is Christian, and we're going to start with the first part of using supercomputers, where I'm going to show you, I'm going to give you an introduction to supercomputers, what are they made of, and a brief introduction on how to use them, how they are shared across researchers, and finally, how to the basic interactions such as submitting programs for execution and understanding how to monitor your jobs and do basic operations such as launching a job, canceling jobs, or writing files and scripts. The only prerequisite knowledge is Linux, because supercomputers run Linux, the operating system Linux. And yes, we are ready to go. And we start with an overview of supercomputers. A supercomputer is an hardware and software infrastructure dedicated to computing. It allows researchers to perform very big calculations. The number one supercomputer by compute capacity is Fugaku. It's shown here as an example. And it is capable of performing 415 petaflops. That is a billions of operations per second. This is several orders of magnitudes more than your laptop. And this is the most powerful supercomputer in the world today. And it allows thousands of researchers to perform their calculations at the same time. Another example of supercomputer is Summit. We are going through some examples just to give you the idea. Summit is a bit less powerful of the first one, but still it's it's the second supercomputer in the world for compute capacity. It's in the USA. More or less every country has, every major country has a supercomputer that is used to boost the research and the science, the public research, but also the classified one. This is because in today's world, the science experiments are mostly run on supercomputers through simulations. For Australia, well, in Australia we have Cuda, which is at the moment the most powerful supercomputer in Australia. It ranks at the position 53 in the top 500 list of most powerful supercomputers. Well, we are going to have here at Pawsey, hopefully very soon, a new supercomputer, which will be more powerful than that. Actually, 50 petaflops of compute power when we'll be ready. But currently we have Magnus. Magnus is a 1 petaflop supercomputer, which has been active for almost 8 years now, my understanding. And so these are just a few of the examples of supercomputers that today are running experiments by thousands of researchers. Today, we are not going to use Magnus. We're going to use smaller clusters that we host at Pawsey. One is Topaz, which is a GPU-focused system. So a system may have CPUs and may also have GPUs. Topaz is a system that, of course, has CPUs, but also provides around 40 GPUs for GPU-accelerated computations. This is an image instead of the first phase of Setonics. So supercomputer is usually delivered in phases due to high complexity. The first phase of Setonics, which will be here, actually is already here, but will be available to researchers next year, will provide 3 times the compute capacity of Magnus. And once completed, it will provide 50 petaflops, as I said, 45 of which comes from GPUs. sounds for who is new to these terms. This all may sound very complicated, but you get the hang of it. So the important thing to understand here is that supercomputers are very powerful, and they are very different from the computers you're using in your everyday life, such as workstations and laptops. The reason is that supercomputers are made to be used by several researchers at the same time, and it has to provide an enormous quantity of compute power. To do so, a supercomputer is made of several, actually many we can say many computers put together. But these computers are not are similar, maybe similar in performance as a workstation, but the architecture is actually very different. A supercomputer has a complex hierarchy. Starting at the bottom, we have the compute plate, which is made of usually on this system, the representative is made of 4 compute nodes, but usually several compute nodes. And the design of these nodes are optimized for taking the least space possible, because these plates are then put together in what we call chassis. Each chassis has around 60, in this case 64 compute nodes, packed together, again to minimize the space utilization, but also try to decrease the energy dissipation, and try to, the whole design is focused on packing together in the least space, least amount of space possible, as much as compute power. And then the chassis are put together in what we call cabinets. Each cabinet, we can see, provides already around 400 compute nodes, that is 400 computers. And finally, a whole supercomputer is made of hundreds or even thousands of these chassis, of these cabinets. And the nodes are then connected together through a very powerful networking infrastructure that we call interconnect. So a supercomputer is not a single computer, a very powerful single computer or big computer, but it's many, many computers connected together to provide a huge compute capacity. From the user point of view, a supercomputer can be abstracted in the following way. We have several types of nodes. The first type is the login nodes that we have encountered already. These are computers, let's say, designed specifically to let the users access the system. Then we have the compute nodes where the actual program, the programs of researchers run on. They are the allocation of compute nodes to the various programs is decided by the scheduler. So since we have so many compute nodes, how you decide which one to use and how to know when one is free or not? Well, you don't know that, you don't decide that, but it's a program called scheduler. The scheduler collects your programs and your requirements, and then finds the best time and the best nodes to execute that program for you. We have then the data movers nodes that are specifically designed to, or they have the purpose of moving in and out of the supercomputers a large quantity of data. Data on the supercomputer is stored in high-performance storage. It's high-performance storage provides a very large amount of space where users can write to or read from at a very high data rate. The storage is visible from every node in the system to provide an easy interface for programs to read from and write to. So as I said, a supercomputer is made of several compute nodes, and that is where the program runs. Each node is characterized by high-end components such as very performant CPUs, very fast memory, and possibly additional hardware such as GPUs. All this hardware in a single node is connected through a very high-speed infrastructure, but also compute nodes themselves are connected to each other through the interconnect, which provides a speed around 100 gigabytes per second. This is a picture of the hardware making up the interconnect. It's very messy, so you don't have to deal with that likely. Well, how you are going to use the compute nodes, or better, how they are best used? Well, the reason you can unlock the high compute capacity or compute power of a supercomputer is to run parallel applications or parallel jobs. But there are several ways of making an efficient use of supercomputers. You may have large calculations that cannot be hosted on a single machine because maybe of high memory requirements or would take too long to compute, way more than the machine could possibly handle. So you divide the problem in subproblems and assign to each subproblems to a different machine. That is one way to go. Or you can see you simply want to obtain the results faster, and so again you divide your problems across the compute nodes to obtain a faster executions. And a third way is when you have several computations to perform, several programs to run maybe, and then you may run these programs at the same time on different compute nodes. So there are different ways, different patterns through which a supercomputer can be used. The fast storage, the storage itself actually is not does not physically reside in a compute node, but it resides in different cabinets. But the storage itself is connected to compute nodes through the same interconnect. It provides, as I said, a large amount of space for users to read or store large data sets and read to and from at a very high speed, at very high data rates. Because if a program runs very fast on a compute node because it's very powerful, but then it's stuck reading and writing files, then we don't go that far. So we need also a very fast, high-performance storage. Compute nodes may also have local storage that is something similar to the storage on your computer, so it's physically attached to the node, but it can be used as a cache or a temporary storage. But the main storage is the main file systems are actually the high-performance ones. This completes the overview, and we are going to now see how you can log in a supercomputer. And we have seen that already, but we are going through again. A login node, you connect to a supercomputer through the login node. The login node must be used to perform administrative work, such as preparing your program for execution, manage your workflows, checking the results, or install software, writing scripts, etc. But it must not be used to run the programs. I mean, must not be. You can prepare your programs to run, meaning you can write the scripts, and that script can be submitted to the scheduler on the login node, but you cannot execute the program as you would on your workstation. you cannot launch your program directly, because if everyone did so, then the login nodes would be overwhelmed by all the programs running on them. We have just a few login nodes compared to the large amount of compute nodes available. This is an example of terminal where now we have seen how to log in on Zeus or Topaz. You log in through, you don't have obviously a screen on a supercomputer. A supercomputer is a big infrastructure in a very isolated room, so you don't have physical access to the supercomputer. You connect to a supercomputer remotely using your own laptop or workstation and a program that implements the SSH protocol, which can be the SSH command or MobaXterm, for instance. And hopefully you all managed to get on the supercomputer by now. If not, you can write on the chat. Someone will help you. This is the first exercise we have. The exercise will ask you to simply log in on Zeus and see if you can perform these simple operations. When you connect on the supercomputer, you will have you will be shown a prompt. If successful, you will be shown a prompt that will accept commands such as cd, pwd, ls, the normal Linux commands you would execute on your Linux machine if you have Linux. But this is running on the login node. These commands are running on the login node, and they are to be used to prepare your workflow and to submit the jobs to the scheduler. I guess I'll give you a couple of minutes to try again this one. I guess I can do it together with you. I'll share my whole screen because now I'm sharing just the presentation. Oh, I think oh, okay. I think now you can see my terminal, right? Okay. Okay. Better?
Yeah, use the whole screen if you can.
Oh, the whole screen. Okay, is better?
Yeah.
Okay.
Maybe even a bit bigger.
Okay. So now I'm using my own account, so I don't have it's the same. If you connect on Zeus, then you have a prompt similar to mine. And if I type the command pwd, it shows my home directory. Unless we show the content of my home directory, I have a few files now. And if I type host name, for instance, well, it returns Zeus1. Zeus1 is one of the login nodes. So to show that we are actually on the login node of the supercomputer. Because this exercise is more to verify that you actually can connect. So I'll move on now. And the second exercise is actually to do something a bit more complicated. Well, no, I wouldn't say complicated, but
Christian, just before they git, maybe they need to change to cd to my scratch, just to be sure.
yeah, sure. So the directory were created, right? So you all can cd to my scratch. This is an environment variable which is defined when you log in, and it's just a shortcut to this directory, which brings you to one of the high performance file systems that we have, which is suited to run intense higher computations, even though right now we are not doing so, but it's always a good practice to write and read your data from the scratch file system. So
While you're doing that, just a reminder that CD is change directory and LS is list what's in the directory. And it looks like there might be a little bit of issues going on with my Scratch. And I think Pascal is doing that in the background.
So the interesting thing is that I cannot copy paste the link from the slide. So I'm going to share the link of the Git directory on the on the chat. Okay, so it's easy for everyone. And so now the exercise with. Okay.
We'll just pause for a moment. It looks like there's something going on with my Scratch. So we're going to pause and have a look at that.
Yeah, definitely.
Let me unmute. All right. So just to make sure, are people typing CD $ my Scratch? Because people are typing, I've seen people type just at least in the chat, just my Scratch without the $, which shouldn't do anything because it shouldn't return anything.
Changing into the my Scratch directory isn't the problem. It's just like whenever, for me personally, whenever I ls, it just completely gets rid of
the ls freezes.
Yeah.
Ah, that's interesting. Okay, so yeah, so the ls is freezing. That's different.
Maybe Pascal, one thing that I think it still needs to be done. I don't know if that's a source of the problem, is to change the ownership to each of them. But I guess that's not.
That wouldn't change. That wouldn't impact ls. So if people are having an issue with just typing ls and it freezes up entirely, I mean, it does suggest that there's been a hit on Lustre with some metadata, probably not caused by us. It could be something else entirely. So let me just have a look here. If you can open up a new terminal, yeah, give it a try.
Oh, actually, ls just evaluated after like 3 or 4 minutes for me.
Okay, so that I can believe that there was possibly something hitting the metadata servers. Maybe something else was going on, but it shouldn't. That would certainly cause ls to hang and wait. It probably wouldn't be us because we're not doing anything file IO heavy. But if it impacted everybody, probably something did happen. I'll check Grafana and see what's there. But
I think this is with the Zeus.
Yeah, it's working now.
Okay, so there probably was an incident. I will check the logs, but it's almost really unrelated to us. So it's good. People can now do stuff.
So I think what's interesting though is that we are working on the live supercomputer. So
Yes.
This is what happens. So when you're working on your projects and something hangs that seems unusual, give it a minute, right? Don't give up on it right away, and try to unpack it, try to think about it, because we are running on the live system. So if there is somebody who hits something with a weird metadata thing or something, that could happen to you, right? When you're running your projects. So this is really important for that. And I think Pascal's got an answer.
So there is at least an alert on Grafana with the Lustre file system. So but not at this time, but it could be that there could be other issues coming up.
So the thing is that when a supercomputer, as I will explain later, it's used by many researchers at the same time. It means that although the file system is a high performance one, it can be still put under high pressure if many users run intense programs that writes or read a lot of file, and sometimes it becomes slow, or the program can hang. and hopefully it's not too common, but it happens. So this is the kind of problems you may have, and that you usually don't experience on your laptop because it's only you who is using your laptop. But on a supercomputer, you always have to keep in mind that many other people are using it at the same time. And so you can have these kind of issues. But if everyone now manages to use or has managed to move to the directory, you can proceed with the exercise. I can give you a couple of minutes and I will do it together with you. So the exercise, go back on the slide, will ask you to download a Git repository. So it's, for those of you who don't know, Git or this procedure is essentially, it's a website. GitHub is a website where we can store code, public code. So, and with this git command, we are basically copying that code on the supercomputer from this website. The command git clone will download the code essentially. And so if I execute the command, I've linked I posted the link on the chat so that you don't have to type it manually. So as you can see, I've cloned the repository or copying the code, and now I have a directory called Introductory Supercomputing, which is a directory we will use throughout the session to do exercises, execute sample programs. So we can use CD to move into the directory, and we can check the content. We have several folders, one for each exercise. Okay. So I'll give you 1 minute and then a couple of minutes, and then I can move on. Just to type in the chat if you have issues. Yeah, I'll put the link again in the chat. Okay. We are going to execute some of these exercises later on.
And just as a heads up, so there is time that you can work through exercises later. So if you feel like you're getting a little behind, please do let us know in the chat. But don't worry. There will be time throughout the day to continue to work through what's going on, to practice, and to get you comfortable on getting in, SSHing in, doing some of the commands, and yeah, we'll make sure that you're comfortable with that. That's a good question. Why don't we ask that one out loud so we get it on the recording? So if something appears on GitHub, git clone with the site address clones the directories into your current directory?
Yes, by default, if you use the command shown on the slides, I will clone the directory in your current directory. We'll clone the repository in your current directory with the same name of the repository. But you can change that by passing an additional argument, specifying the path where you would like the directory to be stored and the repo to be stored. That's from the top of my memory, but you can specify a different folder. Okay. Couple of more seconds, I guess, and then you can try to move on. Okay, so we are at the end of the login slides. The common problems that you may have already encountered is that, for instance, you can your access may be revoked due to many failed login attempts. So if you fail to log in 3 times, well, it's three consecutive times, then your internet address is blocked due to security reasons to avoid potential attacker or any kind of disruptions to the system. If you are in that position and you believe that it was an accident, then you can write to a help desk, to our help desk email, and ask to be unlocked. Other problems may be you forgot your password. Well, not in this case. We are just using test accounts, but when you will have your real account, you may forget your password, and so we have a service to reset the password. Sometimes the supercomputer is unavailable due to maintenance. We are fixing things or improving stuff, and so we need to take away the access from users so that we can work on it. And so if you realize that you are not able to log in, it's maybe because the system is unreachable for the moment. And you can check when this is the case on this web page. We have a maintenance and incident page where we post or we advertise actually earlier the outage.
That's a really good point, Christian. So you're locked out after 3, potentially 3, because it thinks if you do 3, one right after each other room, you will be locked out. But also it's good to keep a lookout, because I think it's the first Tuesday of every month there is some maintenance on the systems. So you want to make sure that you keep looking at the maintenance schedule and don't leave anything to the last minute in case there is a maintenance schedule going on for the supercomputers. Pascal?
I was just going to mention that in terms of SSH, it's not that 3, let's say if you put in the password, you'll try to log in, so you put an SSH command once, you have 3 attempts to put in the right password, it then closes the connection. It doesn't fully block you out, it just closes the connection. It's if you do that SSH command many times, always putting in the wrong password, that it'll then start looking at your IP, and it's also usually key to the rate. So obviously for denial of service attacks or other attacks, the reason why some programs like FileZilla, like transfer programs that people might use that have graphical interfaces are a bit dangerous is because they have this automatic retry if there's a failed attempt, and that automatic retry will try continuously super fast. So for us, it looks like someone's trying random passwords or the wrong password over and over again very quickly. That looks like an attack. And so then it definitely gets blacklisted. If you type in your password 3 times and then get the connection closed, and then you type the SSH command again, and you type 3 times, the password gets closed, you type it slowly. I mean, I would take a moment to make sure you got the right password. If you do it again, that's when it gets an issue. So it's not just 3 attempts, it's 3 full attempts of SSH with the wrong passwords all the time. That ends up being an issue. Also, the rate is a key thing. So if it sees passwords being put in microseconds apart, right, that's a program, it's a bot just putting in passwords. So then it's going to try to block the IP. So the firewall is a bit intelligent about how it blacklists stuff.
With that, there's just a piece of trivia that's very interesting. Cloud, as soon as you set up a VM, a virtual machine on on Pawsey's Nimbus Research Cloud, it's less than a second, and there are bots that are out on the net that are hitting it, trying to get into it. It is less than 1 second, and something recognizes it out there, and it's trying to hit it. So security is a real issue and a real consideration, I should say. So that's why when you're using the machines, you want to keep your passwords. Not these, obviously these are on training accounts that are very, they're separated from the rest, right? They're protected, that you can't get beyond that. But when you do have your password for your projects, you don't want to be giving that out, and you don't want to be giving your username out. Don't share that. Pawsey staff will never ask you to share that. So if somebody asks you to share that, it's not from us. So just keep that in mind.
So to avoid all these problems, you can set up the SSH key authentication, which it's a safer way to communicate with the supercomputer. You can find a documentation at the link on this page. Essentially, you will create a couple of files. One is the public key and the other is the private key. You will copy your public key file on the supercomputer and use your private key, and the pair private public key will be used by SSH to communicate safely with the supercomputer without you being asked for the password. Obviously, do not share your account. You're not allowed to share your account with other people. It's only to be used by you yourself. And again, do not provide your password to anybody else. You can access the supercomputer. We have seen is used through the command line, so there is no graphical interface usually. We have, however, for some applications, you may need to visualize a large amount of data, and we have, for that purpose, we have a visualization nodes. They can be accessed through a graphical interface, but it's only limited to those use cases. So visualizing large amount of data with specific programs and for a specific set of nodes. But usually, if you want a graphical interface on the compute nodes in general, you may need to use the SSH GUI forwarding capability -X if you want to open a program with a graphical interface on the supercomputer, but just for the lightweight ones. Usually, it's not advised for you to run programs with a graphical interface, not on the supercompute nodes, unless in very specific cases, such as debugging. But for the time being, just consider using the supercomputer only with the command line. Now, the second part is sharing supercomputers. As I said, supercomputers are used by many researchers at the same time. This is because the infrastructure is very big and provides an enormous amount of computation, so can be used by many people and should be, because running a supercomputer is very expensive, consumes a very large amount of electricity, and whether it is idle or not, there's still consumption. So the best use of it is to get it at full capacity as much as possible. That means also having jobs running or programs running nights and weekends. And since we want to achieve that objective, and we have many users running many programs with different characteristics. Some users may run very large jobs using a lot of CPUs. Other users need a lot of memory, and etc. We have different usage patterns. Running programs on a supercomputer requires an orchestration. That orchestration is provided by the so-called scheduler. A scheduler is a program, and Pawsey uses the SLURM scheduler. is a program that takes the requirements and the program to run from every user, and then decide which program to run at any given time with which priority. Users, from the user side, there is the so-called job preparation. The user selects the program to run and describes the resources needed to do so. Then gives this information to the scheduler through a script that we call batch script or job script. On the scheduler side, we have many scripts or many jobs to be run. So the term job refers to a program together with the requirements needed for it to run. So the scheduler has many jobs to run and has to decide which one to run at any given time. Well, it can run all of them if there is the capacity, but most of the time there are so many jobs that the supercomputer cannot run all of them at the same time. So some jobs need to wait for their spot, the supercomputer. The job of the scheduler is to optimize the usage of the supercomputer, that is fill all the compute nodes, or as much as compute nodes as possible. And at the same time, it needs to provide a fair waiting time to all the users. So a user must not wait 3 months for his job to run. What we have is that from the scheduler perspective, the compute nodes are divided in partitions. This is because we may have some nodes with some characteristics and other nodes with other characteristics. For instance, some nodes may have only CPUs, other nodes may have also GPUs, other nodes also may have a higher quantity or amount of memory available. So based on the compute node characteristics, we have different partitions. But to each partition, we have an associated queue to which users can submit jobs. So if a user has a program that needs a lot of memory, can submit a job to the high memory queue. Or a job needs GPUs, then the job can be submitted to the GPU queue. So in this picture, it's a rather, at first, messy representation of the utilization of a supercomputer. On the x-axis, we have the start and end times, we can see, or the timeline. And the y-axis, we have the CPU IDs. And each color rectangle is a job which spans a certain timeline, a certain interval in time, and a certain range of CPUs allocated to it. And we can see that the scheduler tries to fill in every gap in the graph. So we have many jobs running at every point in time. The key point here is that your job may not run instantly like it happens on your computer, but it may most likely waits in the queue for a certain amount of time, can be hours or sometimes even days before it runs. And so you need to automate as much as possible, write your scripts such as that it's ready to execute at any point in time, and then go and do other stuff. You don't have to wait in front of the screen for your job to start. I'm going to introduce some terms that are used when we talk about SLURM, or when in general we use the supercomputer. Or for instance, more importantly, when you read the documentation, you may find Pascal as a question or as something to say.
Just something to say, which is that apparently the ICRAR people at ICRAR Curtin had a fire drill, so they were away for 10 minutes because they had to leave their laptops behind while their fire alarm went off. So if we can do a quick recap of the last maybe 3 slides
Oh,
for
yeah,
the ICAR
definitely.
people?
I'm sorry for them. Hopefully, well, luckily it was nothing. So as I said, I was saying that a supercomputer is shared among thousands of researchers, and so there is the need for an orchestration of the programs, the execution of the programs, and users so write scripts. Users write scripts where they specify the program to run and also the requirements for it that it needs to run. And the scripts then are submitted to a program that is called a scheduler. A scheduler is a program that takes the various programs that are submitted by the researchers, or the various scripts submitted by the researchers, and then tries to optimize the use of the supercomputer in a sense that it tries to run as many jobs as possible, trying to fill in all the space or all the compute nodes, and at the same time it tries to give each user a fair wait time. So the scheduler also tries not to make the user wait a long time for his or her job to run. So there are the work of the scheduler is rather complex because it has several objectives to optimize. That is, fill in the capacity of the supercomputer and give a fair treatment to every user. The scheduler partitions the compute nodes in different sets. These sets are well partitions, and each partition, and it is done in this way because there are nodes. Compute nodes are not equal. May or may not, but usually we have different sets of compute nodes with different characteristics. Some compute nodes may have a higher memory available, or may have GPUs. Other nodes may have only CPUs. So for different types of jobs, we have different types of compute nodes that can support them. To each partition, we have an associated queue to which jobs are submitted to. In this picture, we have a representation of the scheduler program, let's say, or the schedule, actually, the schedule of the jobs. And we see that on the x-axis, we have the timeline, and the y-axis, we have this allocated CPU cores. And each colored rectangle is a job that is running on the supercomputer. And the scheduler does a good job to fill in the gaps. Each gap is idle time that can be used by a job, if possible. The key point here is that you need to prepare your program for execution such that you don't have to wait in front of the computer for it to start and check on its progress. You need to automate as much as possible, such that you can submit the job to the scheduler, your program for execution, and then go away from the screen and come back whenever to check how it's going. But the job needs to must be able to execute autonomously without user interaction. I'm going to introduce now some terminology that is used throughout our documentation. It's common terminology across supercomputing centers. So as I said, a partition is a set of nodes with an associated job queue. Each partition characterized has some characteristics. Some partition may have a longer work time, or allows a program to run for longer times, or gives access to a higher quantity of memory, as I said. A cluster is all the partitions, and usually corresponds to a supercomputer. So sometimes you can here a person calling the supercomputer a cluster, or vice versa. It's basically the same thing. Now, as you can interact with the scheduler with several programs. So I guess if there are any questions, this is a good time to ask, and you can write in the chat and someone will read out loud the questions maybe. But you interact with the scheduler. So the scheduler is a program running on the supercomputer, and you can interact with the scheduler with several commands, several Linux commands. The first one that you're going to see is the sinfo command. The sinfo command is used to explore the characteristics of the cluster at any point in time, or at the time you call actually the command. And usually use the sinfo command when you are logging on the login node. All these commands must be run on the login node. I mean, can be run on the compute node, but usually you run on the login node. And the sinfo output is shown in this slide. The sinfo shows the, oh, yes, Pascal?
There's a good question that probably is good to record, which is what's the difference between a partition and a node that you run on? So that just making sure what's clear, what is a node and what is a partition?
Yeah, definitely. So a node is actually the physical computer which will run your program, and it's a single entity. It's a computer. A partition instead is a set of nodes, and a partition is somehow an abstract concept. A partition is a concept defined in the SLURM configuration. And a node, several nodes may be part of a partition. So each node, by definition, each node is part of a partition. And a partition, so it's a set of nodes with common characteristics. So for instance, there is the partition with high memory, where each node in that partition have a larger quantity of RAM available with respect to other nodes. Other nodes may have GPUs, and so those nodes are collected in a set of all the nodes having a GPU. So if you have a program that needs a GPU, then you don't want to submit that program to a node that doesn't have a GPU. You want a node that has a GPU, and so you're going to submit your job. You're going to tell the scheduler, run this job on one of those nodes that has a GPU. And to do so, you say, queue the job on the queue associated to the nodes having a GPU. So it's a way of classifying compute nodes, the partition. Hopefully this answers the question. And the set of all partitions, it's basically forms the supercomputer. And the sinfo command shows actually exactly the partitions of a supercomputer. I've run this sinfo command on Zeus, and what the output is the following. We have a row. We have a row with several rows with several information. The first column shows the partition. Well, each row actually represents a set of nodes that are in a particular partition and that are in a particular state. For instance, the first row tells us that some nodes in the work queue partition are available, and they are in the mixed state. It means that each compute node in that partition is partially used. There are some free resources and other resources are allocated. Instead, the second row tells us that other nodes, actually 26 nodes in the work queue partition, are allocated. It means that those nodes are fully booked. no other job can run on those nodes at the moment. The third row tells us that the 36 nodes in the work queue partition are idle, means that they are not utilized and they can accept jobs. And we have this kind of classification for each partition. So this gives you a view on the status of the supercomputer. I typically use this command to see, okay, there are nodes available for me to run my job at the moment, or how long, or what are the characteristics of each partition. For instance, we have that you can see that for the work queue, you have a time limit of 1 day. The time limit is the maximum amount of time your program can run for. And the long queue, for instance, is a good example of how partitions are used to distinguish between among nodes with different characteristics. We have a long queue, and it's called that way because it allows up to 4 days of execution time. The high memory queue has a higher amount of memory available, which is not shown in the default output of sinfo, but you can customize the output with several options. So you can see the CPUs, the number of CPUs available on each node, the number of nodes in the partition, and also the various host name of each node in the partition itself. So basically use this command to see what partitions are on the supercomputer, how many nodes are there, how many cores, and what is the time limit. As I said, for each partition is created because we have nodes with some characteristics that we want to group together. And each partition has a reason to be used. The work queue usually is used for the production jobs, the jobs that you want to run for several hours. You may want to develop or test some codes, then you can use the debug queue partition, which has a smaller time limit, but allows for a fast turnover, and etc. We have several queues with several requirements, with several characteristics. As I said, jobs are not executed instantly, but are put in a queue. So for instance, you submitted a job in the work queue, and you want to check how many jobs are waiting together with me. Well, at the moment, you can query the list of all the jobs in the queue using the SQ command. The SQ command will show you, and here is the output, will show you the list of jobs that are queued in a particular queue. So you can have a sense of how many people are waiting together with you, how many jobs are waiting to be run, essentially. And in particular, SQ will show both the jobs that are waiting, that are the state is PD, so pending, or jobs that are currently running. So the first 3 jobs in the output shown here are running, and the others are waiting. So for several reasons, some other jobs are waiting because there are not enough resources. Other jobs are waiting because they have not enough priority. Other jobs have a larger priority or a higher priority. So SQ command is useful to see what's the status of the queue, how many jobs are there, and how much you're likely to wait. And SLURM will also provide you with an estimate start time. So you have a start time or an end time. You can see that for the 5th job, for instance, it says that your job will likely start tomorrow at a certain time, but these are just rough estimates. It can change. You can filter the output of SQ. Oh, Pascal, some comments as well.
It's just to mention that the current systems at Pawsey, if you type SQ, you can kind of see the entire queue. But going forward, there'll be filters so that you can never know what the queue is like in its entirety, except for your group. because and there are other clusters as well that are moving towards kind of not being able to see how everybody else's jobs are running. Because if you are not part of the group or not part of the, like in collaboration with that particular user, whether you should have a global perspective of the supercomputer is an open question. There's also privacy as well, like what jobs could be running. So if somehow you guys going forward eventually manage to get on Photonics, SQ will behave differently. You will not be able to see everybody just typing SQ and looking at all the jobs that are running or in the queue. You'll see essentially either your jobs or the group's jobs, and that's it.
Yes, that is a good observation, but still SQ will be useful because provides you tells you whether your job is running or not, or provides you an estimate of when it's going to run and why it's not running at the moment. Even here we have several fields. We have the job ID. Each job is given a unique ID you can use to query information about the job, the user who submitted the job, the group or account, the partitioner, etc. I hope you can try these commands as we go along. I think it should be fairly easy. If someone has a problem executing these commands, please write in the chat. In fact, we have another exercise, and I can give you a couple of minutes to practice with the command. Yeah. So in the meantime, well, I can show you the commands that we have so far. We have done so far. Sinfo, for instance, this is on Zeus, and we have this configuration. And now if I log out and I go on Topaz, I have my own SSH configuration so that I don't need to type the password. And now I go on Topaz and I again type sinfo. I see a different output because now I am on another supercomputer. And so I see different partitions. I didn't need to go to log out and log in again because there is the option -n through which you can specify the cluster you're interested in. So for now, at that time on Topaz and I type this command, Zeus, I see the status of Zeus from Topaz, and we can compare. So we can see that there are some partitions that are not available there are some partitions on Topaz that are not available on Zeus. For instance, the GPU queue. This is because Topaz has GPUs, whereas Zeus doesn't. The NVLink partition is for a special type of GPUs with a special interconnect. But the point here is that we have several partitions and several supercomputers because these supercomputers different in the usage and use cases that they support. Now I try the SQ command on Topaz, and I see that there are a lot of jobs submitted to the GPU queue. Well, it's the main queue used on this supercomputer. But we have also another partition which is called acceptance. Apparently, our admin are running some tests on the supercomputer. So you can see there are a lot of jobs running, but also a lot of jobs waiting to be run. And there is and you can see why they're not running by looking at the column that is called reason. The reason they're not running is because maybe the request node is not available, or there is a dependency that is another job has to complete its execution before this one can start, etc. So the output is a bit as you can see now, I am able to see the users who are running these jobs, but for privacy reason, I shouldn't be able to do so because I may complain this user is using all the supercomputers, but no, it's the scheduler has decided, so we cannot do. It's the scheduler job to schedule jobs, not ours, and we leave that job to it. And hopefully you have managed to have this kind of output. So if you sometimes you just want to look at your jobs because you want to look at the status of your jobs and you're not interested in the others, and then what you can type is SQ --me, which shows you, and it will show you the jobs, your jobs in the queue. Currently, I don't have any job in the queue, so I see no output. Okay. So sometimes you can see that with SINFO, sometimes you will see that some nodes are down or drained. These are particular states that basically indicate that the nodes are not available for several reasons. Sometimes you can see that one node is reserved, and this is reserved because we are currently having a training and we took that node and we reserve for this training. No one else can use it except us. Okay, we can move forward if there are no questions. We can have actually, maybe we can have a pause at this moment. It's been 1 hour running. I guess we can have a pause at 10 minutes pause, and then we can go back to the training. This is a good time to break. Okay, so in 10 minutes. Okay, here we are. Hopefully everyone is back. And everyone has had a successful attempt at this exercise. And so we can move on to the next topic. Well, are there any questions on the previous exercise? I don't think so.
No, most of the questions that are answered are SCH.
Okay, so the next topic is the allocation. So how you get access on the supercomputer in terms of, oh, sorry, my video is not, okay, my video is on. The next topic is about project allocations. That is how much compute capacity you are given on the supercomputer. So the supercomputer has a huge compute capacity, but it's still finite. And it needs to be partitioned across users in a fair way. The first step is to define a measure for the compute capacity, and supercomputing centers came out with the definition of service unit. So a service unit is usually defined at a very basic level. It's usually defined as 1 hour use of one core or one CPU core. If you have accelerators like GPUs, then you can define have additional definitions such as 1 hour use of one GPU is equivalent to 36 service units. But the point here is that once you have this definition in place, then you can quantify the amount of compute capacity available throughout the year on a supercomputer. And the unit of measure is the service units. So as a rough estimate, you can think of as the total number of CPU cores on the supercomputers multiplied by the total number of hours in a year, and that gives you the capacity of the supercomputer in service unit. Then what we do, we need to partition the quantity across researchers every year. That is, each research group gets an allocation of those service units, a portion of the total compute capacity. The way we do so is through a merit allocation process. Each year, a user or research group applies for time on the supercomputer and gets a certain amount of service units. At Pawsey, we partition furthermore those each allocation in 4 parts that are equal in size, and that corresponds to the 4 quarters of the year. Each unit to consume each quarterly allocation within the quarter, otherwise is gone. This is to incentivize user to say spread the use of the supercomputers across the entire year, and not to use the supercomputers only at the end of the year when they remember or have an allocation to use. This is because otherwise the system would be too congested to be used. Also, the amount of service unit you have available, the amount of allocation you have used influences the job priority. That is how much time that your job waits in the queue. And it's, for instance, if you have only used a small fraction of your allocation, then the scheduler will more likely give you a higher priority than other jobs of projects that have already consumed a huge part of their allocation. We also favor large jobs, that is jobs using many cores, because that's the best use of a supercomputer running programs that cannot be run on normal computers. You can check, once you have an allocation, you can check the balance, so that is the amount of service units you have left, with the Pawsey account balance tool. And here it is shown an example. An example is shown about how to check the amount of service units that are consumed for the Pawsey 001 project. So there is a question about service units, right? You told me. So good.
John did have a question.
John, I mean, I remember seeing Alexis commented that you can unmute. Do you have a question you want to ask?
I was actually, I think Danny put a question in the chat as well about the priority column in when you did sinfo or one of the other, sorry, I forgot which command it was, but.
Yeah, so the sinfo, if you look at the priority number, the number itself is it's only useful in terms of relative. So it just tells you relative what your priority is relative to other jobs in the queue. So if you saw a number of 6,000, it in itself is informative. It's the priority relative to other priorities by SLURM, and the priority is dynamic. So it will increase as time goes on, but also if you had a low priority, but suddenly there's a really easy slot to fit in that job, and it's short, it might fit it in. So the priorities are indications. Higher priorities are more likely to be scheduled than lower priority jobs, but obviously it also depends what Tetris you can do with the job's resource requests, right?
Okay.
So higher priorities indicate that it's more likely to be scheduled, but there's no value at which you suddenly go, I know I'm going to be the next job running. The priorities kind of give you, and the start time, give you an indication of when you expect to start and what priority you have. But that's essentially it. And they're not consistent across clusters, right? Like the priority values are varied between clusters. So if you look at it.
Yeah, one thing I want to add is that you actually can have a breakdown of that priority value.
Yeah.
There is the command as prio, here the auto completion helps me. That gives you a, if we open the month page, it tells you that view the factors that comprise a job scheduling priority. So you can see the various reasons why your job has that priority. So I'm not sure I can see the priority of other jobs. Probably I can. You can give it a try. For instance, we have, if you go in the queue,
Can you increase the size of your window?
Oh yeah, you're right. Maybe decrease the size of the fonts. So for instance, let's just take this job. And then I do as prior dash J, that stands for, oops, for the job. Unable to find jobs, so probably because I cannot, it's not my job, and so I cannot of course pick into the other job, but essentially this will output breakdown of the various components that make up your priority. But I don't have a quick example to show because I don't have any jobs running at the moment.
Yeah, okay, that's cool. If you don't mind, I was also going to ask if you could repeat what the up and down in underneath available meant.
So up means that the node is up, means that it's working.
Okay.
Means that it's functional.
Yeah.
Sometimes it's
yeah, like the
it's
partition.
complicated. So it means that it's available. It means that it's actually in the partition, like it's available to be used, the partition. But then we have, as a partition, then we have you can have at the compute node level, you may have several states there. So the total partition, for example, the GPU queue is up in general, so it's available. But then you have one node that is down because some reason, maybe there's been some maintenance or something. One node is reserved, but then you have other nodes that are mixed or allocated, which means that they're currently used by users. So the whole partition in general is up. You can use the GPU partition, but your job will likely be allocated with the schedule on the one of the 5 mixed nodes at the moment, if enough resources are available.
Okay. Yeah, that.
Instead, the other, yeah, the NVLink queue partition instead is done, means that all the nodes are not available, so the entire partition is actually down. Hope that answered the question.
Yeah, it did.
The second part is submitting jobs. So how do you actually run a program on the supercomputer? So as I said, a job is your program together with the requirements for it to run. And the main way is writing a script that specifies the way you want to run your program, but also the resources required. For example, number of CPU cores, amount of memory, which partition to use, and etc. Once you have that script, I'll show you in a second how to write it. You submit it to the scheduler with the sbatch command listed here. SQ, we have seen the command, and scancel is actually will tell the scheduler to actually not execute the job anymore, and if it's executing, cancel it. These are the main commands to interact with jobs. As I said, once you submit the job, you have an unique identifier for the job so that you can query information about the job. The script, you specify a job using a script, which is a bash script typically, or a CS script. But we advise using bash. And essentially, it's made up of 2 parts. The first part that are bash comments. They specify. Let's see if I have an example. Yes, here we specify the resources. So these are bash comments. So bash won't interpret them, but SLURM will. And in particular, through the syntax, you can specify several properties, such as the job name, which gives a job which gives a name to the job, and it's easier then to find the job in the SKU output, for instance. Then you can specify the account. So which account will be billed for this run? So each account has an associated service unit amount available, and that account will be billed for the job. Then the most common properties are also the number of nodes requested, the number of tasks to run per node, that is the number of processes to spawn per node, and the CPU, the physical CPU cores assigned to each task, and etc. So this is the syntax to specify the resources, and then you can write your script. This is an example, and you can proceed writing your script in a way that then executes your program. This is a very simple example, and we are going to just execute the hostname command for here 20 times. Each 15 seconds, we execute the hostname command for 15 seconds. You can see that each script needs to start with the shebang line, that is specify which shell is going to interpret the script. Then you have the comments with the requirements. Each comment needs to start with the SBatch keyword, followed by the options. You can check the options are available for the SBatch command using the man page of SBatch, but these are the typical ones. So in this example, we are running a single process on one node, and the execution time, the time limit is 5 minutes. We are going to also use the reservation we have in terms queue, so that the job will be assigned to a node in the reservation. I'm going to explain reservations in a few seconds. But this is it. This is our first examples, and let's see if we have. Oh, we have the exercise. But first, the nodes on the reservation. So we have spoken about partitions. That is a way of grouping nodes, but we have also reservations. A reservation is essentially taking those nodes and reserve those nodes for a particular purpose and for a particular set of users. On the other hand, partitions are available to all users of the supercomputer, so they are, you don't know who's going to get the access on the partition at which time. On the reservation, you actually know the users that are allowed to run on the nodes in the reservation. Usually, in our case, we have a reservation called interns queue, and just the people in the interns queue group, that the people that are in this training, can use the nodes in the reservation. So it's kind of a partition, but it looks like a partition, but its access is restricted to a certain set of users. And we can specify the reservation using the reservation -- reservation option. Okay, finally, each job has an associated output, that is the standard output, the standard error outputs that you normally have on your computer as well. The output will be written and redirected to the file, to a single file by default that is called SLURM - and the job ID. And this collects the output from all the processes. So as I said, you can run a parallel program, so different processes, and the output of each one of these process will be redirected to this output file. This is the first exercise that where we are actually going to submit a job to the scheduler, and the exercise is present in the repository we have downloaded earlier in the intermediate supercomputing, or introductory supercomputing, actually. I'll go on Zeus. So what it asks you is to essentially run a script present in the folder, which is called hostname.slurm, and see what happens. So it's basically practicing how to use the sbatch command there. You already have the script there. You just need to submit it to the scheduler. Then you can check the status of the job using SQ, and then you can finally you can check the output by printing the content of the output file. So I'll try to do this exercise together with you. Okay, so introductory supercomputing, hostname, and we have 2 files. You should use the actually hostname.slurm. The other file refers to another scheduler that we don't have anymore, so we probably should delete it from the repository at this point. But anyway, so let's take a look at the hostname.slurm. And we can see there is actually something to be modified in this script. The reservation for today's course is not called Q, but it's actually called interns Q. So if I leave it that way, course Q, and try to submit this job, what happens is, let's see what happens. If I use as batch, it,
Course is another entry.
yes, and that says the fail, its job submission failed, and the reason is requested reservation is invalid. It means that does not exist. This is because the reservation for today is named interns queue. Okay, so if I modify this and try again, access denied to the reservation. This happens because my account is not in the reservation. So the reservation now is valid, but I cannot submit the job within the reservation. But you should be able to. So how can I solve this issue? Well, I can still submit jobs because I'm a user on the supercomputer, but I cannot do so through the reservation. I cannot use the reserved nodes, but there are still other nodes available. So what I can do is just say, I don't want to use any reservation. I might be waiting a bit more, but that's okay. So reservation, and to do so, I just leave the reservation field blank. So what I'm doing now is instead of specifying the option reservation within the script, I can override the content of the script by passing the same option to the sbatch command. In this way, this option has a higher priority than the one in the script. Okay, and so now it says submitted batch job and the ID. Now the submission succeeded. If I do SQ me, it says that it's running. This is because it's a rather simple job, and there was a node available. I just requested 1 core, 1 node, so it was available, and my job is running straight away. If I check the output in the folder, I can see that if I check the folder, I can see that there is already an output file and with some output. And we have the date, the timestamp, because we call the date command in the script, and then we print the host name. So since you are running on a single node, the host name will be always the same. But what happens now, you can try to, again, to submit the same job. And again, I override the nodes option. Instead of requesting 1 node, I request 2 nodes. Now at this point, I have another job with another ID, and then another output. And in this case, I should see something different. It's the same host name. you need. So this one has 2 nodes available. It's running. Task per node. Needs to check again the output. Interesting. I would expect to have different host names. So, well, let's see the reason why. Maybe that the other is still sending the output to the file. So I'm not sure yet, but how is it going to you? Have you managed to submit the reservation? Is there any question I can answer in the meantime? Oh, I see that. I know the reason. The reason is that I need to run this command. Yeah, now I need to run the command on multiple nodes, and to enable parallel computing, I need to use SLURM. So what I'm saying now is that I'm launching the hostname command on 2 nodes. So on 2 nodes here, and tasks basically repeating what I have above per node 1. It's just some experiments. I can set the other jobs in the queue. And now I delete the output of these ones. So this is just to show you some stuff, but it's quite advanced and will be shown later. Oh, okay. Clearly, I need to again submit this. Okay. And now I can see 2 host names. So I have enabled parallel computing on 2 nodes. I will explore these options, or Pascal maybe will explore these options later, but try not to waste too much time now. There are other commands you can use, but the SLURM provides. As control show job will show you some information about the job. The more you use the supercomputer, the more this will make sense to you, but it's a way of showing some properties of the job. We have tried the SQ and scancel together. I guess I'll give you 1 minute to try these commands as well. Then what we have, you may have some outputs, some errors, and those errors will be shown in the output file. Some common errors may be segmentation fault, because that is usually due to invalid memory access or not enough memory assigned to the job. Common error is the time eating the time limit. If your program runs for more than usually 24 hours or the time limit you impose, the programs will be killed, and you will see this error: no job canceled due to time limit. This is very important to know, because your program needs to be able to save progress and start again from the last save checkpoint. This is one of the things to know about the supercomputer and how to use it, and how it differs from using your laptop. You have a time limit. This is to give a fair treatment to every user, not to monopolize the supercomputer for too long by user. Other exercises explore the various combinations that I actually shown you, passing the options through the command line. You can specify different partitions. As you can see with the wrong reservation, I got an error. Not being part of a reservation, I got another error, and etc. So if you have questions or doubts, I can answer those. But essentially, yes. The final command, a very important command that is saccount. Once your job has completed, you don't see it anymore in the queue because it's completed. But you can still retrieve information about it using the saccount command. With saccount, you basically access the database of all the jobs that you have executed or are executing. And you can display similar information to those you can see in other commands. For instance, job name, how many CPUs were allocated, how it ended, which code completed, failed, out of memory, etc. We have, I know this is a lot to take, but we have a good documentation. There are links posted in these slides, but you can also find on Google, there's the Pawsey Supercomputing documentation that will go through each of these information step by step and more in depth. I guess with that, I finished this part, and if you have questions or some doubts about the last exercise, we can discuss it. And check the chat, I guess. Yes, you can use SLURM to send. You can get SLURM to send an email. There is actually, if I'm not mistaken, the email option where you can specify your email, and then SLURM would send an email when job was completed or there is some kind of an update, an error occurred, or the job has hit a time limit or stuff like this.
Also when it starts.
Oh yeah, of course, when you submit a job, it may not start straight away, so you get an email when it starts as well. So any other, if there are no other questions, but I think we have there is a lunch break at some point. I guess starting from now for 45 minutes or even 1 hour.
I guess it's dependent on what people feel like. So 45 minutes to an hour, I'm happy with an hour. If people want to come back earlier, that's okay. But an hour takes us to 12:30, and that is fine for 12:30 to 2:30. Danny asked, could you show the updated hostname file?
So, okay, the updated hostname files is this one. So to run the hostname command on multiple nodes. So just to be clear, let's say that I specify also here I modify the number of nodes here so that it stays in the script and you don't forget to put the command on the command line. An important thing of job scripts is that allows your allow you to have a reproducible environment, so that if you put all the requirements in the script instead in the command line, then you don't have to type them all over again. So you modify the command lines options are good for a quick change, a quick check, but it's better to write all your requirements in the script once they are stable. So in this case, I say I want 2 nodes, and I want for each node 1 task. So task per node equal 1, and each task, or in this case, task is kind of MPI term for process. So task in our case, in this case, means process. A process is a program in execution. Each process gets one CPU. So in total, we have one task on each node, and each one has a CPU. And then now what we can do is, now what happens is, if I didn't put SRun, then the program hostname would have been, not all the resources were used, but the hostname was executed only on the host that was executing the script, the entire script. But to enable the use of multiple nodes, you use the command srun. Srun enables what actually srun does is to create multiple copies of your program and sends those processes to the various nodes as you specify in the options. For instance, I say to srun that I want this program hostname to run on 2 nodes. So what I do is saying run on 2 nodes, and for each node you just run one task. So what I'm saying is basically I'm repeating what I've written in the requirement specification, but sometimes this doesn't have to be this way. That there is a reason why you can again repeat the requirements, because you may want to run 2 different programs. On one node you may want to run a program, on the other node you want to run another program. For instance, I can copy this line just quickly, and now I say this srun instance will only execute on one node, one task on that node, and it will be hostname. Instead, the other instance of srun will launch I don't know, the date command.
Yeah.
Let's say let's say the date command. So we delete this one just to make it clearer. And now if I submit the job, yeah, always the problem with the reservation. So what I do essentially here, I delete this line because I'm not in the reservation, but you should be. So this is a problem that it's only about my username. I'm waiting for the output. Oh, right. That's interesting. Let's see the output.
Because there's 2 total tasks.
Yes, tasks per node, but I specify just one node here.
I think you want to do also n tasks equals 1.
Yep. So let's try this one. It's quite complicated. So another thing to do, you can ask is, instead of tasks per node 1, you can actually say the total number of tasks I'm going to run on every node can be 2. And since we want to run one task on each node, then you can have this kind of formulation, which to me is kind of clearer, but you can experiment with the combination. It's done. And now I have the job running, and hopefully it's okay. Okay, and see now we have one one node will output the host name, so we have only one host name, and the other node will output the date.
So Boom has got a request about GPUs and this batch.
Okay, so I guess that question will be covered in the second part
Yeah,
of the course. But I don't know.
I was going to say that there are there's essentially keywords as well that can provide a GPU request. So you can specify something that says, I want a GPU resources of something. And there is an example in the folders in the vector add folder of GPUs, but we'll get that later on this afternoon. My suggestion is, unless there's a very pressing questions, we take a break because we've gone through for quite a while, and we will come back. I guess we'll have a 15-minute break. So we'll come back at 12:30. So it's a good start time.
Thank you, everyone.
All right. See you guys in about an hour. So 15 minutes because it's 11:40. I'll just put that in the chat.
Okay. All right, here's a question we've got. Well, is there a difference between tasks and processes?
So I will touch that in a little bit, but there's differences in terms of tasks. Tasks, at least as far as SLURM is kind of related to MPI, and processes are related to just any type of process. But I'll go into those details as we try submitting jobs and putting in sort of give you an understanding of how you want to tailor your resource request given the parallel processing that you want to do. I think we might be at almost everyone back, because I remember seeing 44, so I see 43. And given the amount of material that we have to cover, I think I will make a start of it. So let's do. Okay. So welcome back, everybody. This is part 2 of the using supercomputers, and the goal of this obviously is to give you some familiarity with actually being able to run jobs and understand how you would want to interact with a supercomputer. And in this particular set of part 2, I'm gonna talk about the high performance storage, albeit somewhat briefly. And I should mention as well that going forward, the newer supercomputer will have another different type of high performance storage. I will mention it briefly, even though it's not in the slides, simply because it will be later on down the track that this will become accessible. Then we'll actually talk about running jobs, and hopefully give you a sense of how to use the material that's in running jobs in real world HPC. So thinking about how you're actually going to use it. And I feel free in that section, right, to really ask lots of questions of like, well, I want to do this. How do I go about doing this? Because this is my real world HPC application. Okay, so high performance storage. This was asked at the very beginning, and of course, you may have in your laptops, computers, SSD drives, so solid state drives that are quite fast, but they're tailored to individual user access. So not multi-user access, not many different users writing different tons of files at the same time. And so that is where Lustre and a few other different types of file systems come in for high performance storage. So supercomputers have this global storage. Is meant to be very fast, and the fastest global storage with the largest amount of sort of storage footprint is typically Scratch. So it's meant to be short-term storage. There's the idea of long-term storage at least at a supercomputing center is not something that really is done, because we want people to kind of process stuff, produce data products, and if they're really meant to be long-term, as in, stored for years, typically there are other ways of doing that. So we usually don't have that direct access in terms of supercomputers. The idea, of course, for these storage systems is that they're meant to be accessible through all nodes. So all compute can write to the storage, and specifically /Scratch, which we saw a brief introduction, is a temporary working area. So it's meant to be fast, temporary working. There is some of the computers at Pawsey, but not Zeus and Topaz, have like very specific local node storage. So this particular node storage is only accessible actually via the node itself. You can't even have another node access it, and they're not shared with other users even outside the job. Now, the key example of this storage that you guys will have access to in this training session, but also going forward, is Scratch. So /Scratch. It is shared all by all users. You have a quota of 1 million files. And it's really designed optimally for, and not necessarily lots of small files, but lots of moderate and large files, because the storage system for fast access to files, which are distributed across multiple hard drives, right? So the physical hard drives, the files are split across everything, is that they have essentially a metadata server. So they have servers that are running to figure out where files live and brief bits of metadata. So the LS that took a while this morning typically happens if you have a long wait time for LS, possibly because something is hitting the metadata servers and writing an enormous amount of files, reading an enormous amount of files. Some user is doing something that slows down querying the metadata servers of Lustre to tell you what's in the directory that you happen to be supposedly located in. So we have this directory, Scratch project name, username. And so that's in the environment variable MyScratch, which you've hopefully copied the course material into. And the idea is that Scratch is really not meant to keep stuff. So there's purged after 30 days. A file is not touched after 30 days, it's removed. The idea is not to just like move data or rename files so that you can get around this. If they really need to keep it, then it should be moved from Scratch to somewhere else, like group or offsite storage. So you have to make sure that you move or delete your data before it's purged. Really important. There's no backup here, right? So if the data, once the data is gone, it's gone. You can't ask, oh, can you undo the delete? That doesn't happen. We undo the purge. So transferring data, talking to this storage. So we actually have data mover nodes specifically designed for fast external connect. So they can actually then talk to these data mover nodes that will then allocate a job. I see Christian has raised his hand. Oh, okay. What is, yeah, 30 days of not using a file, as Alexis said. So if a file is untouched, unmodified, and is living in Scratch for 30 days, it's gone. There's an automatic purge going on all the time, kind of looking to see what old files exist and removing them to free up space, right? Because, so the idea for Scratch is shared. You can write lots of files as a user. You can have also access to lots and lots of data. So it's, you know, if you needed to save 600 terabytes of data on Scratch, that's fine. If it's 600 data in a million files, 600 terabytes in a million files, that's also fine, but it's meant to be shortish term, right? Okay. So transferring data, because again, let's say you want to transfer 600 terabytes of data in a million files to Pawsey. You don't want to sit there and wait with FileZilla and so on. What you can do is put in requests if the data is accessible, let's say not on your laptop, but on some server that's up and running all the time and that you need to pull data from. Data mover nodes are a great way of essentially pulling data in, putting in a request saying, I want to copy something, and the data mover nodes will handle that copy, set up a connection, do parallel pulls, and then move stuff to wherever you want it to in the local storage system. You can obviously pull and push from these data mover nodes to outside resources. But also the data mover nodes are a great way of handling information. Oh, there we are. So an example of transferring data, at least at the command line. So here's one where you can use GUIs as well, like FileZilla, CyberDuck, etc. But the example here is just to do a command line SCP, so secure shell copy of some file to wherever you wanted to. So you have the HPC data mover nodes, and you can also copy a file using the data mover nodes. So it doesn't clog up access to login nodes, trying to do some transfers. And I will read it again just because it has at least blacklisted people accidentally before. is that if you are using things like CyberDoc, like Winzilla, FileZilla to transfer data from your local computer to Pawsey, if you've got the wrong password and you have auto retry, it will almost certainly cause you to be blacklisted because the program will try retrying all the time, like super quick, and eventually you'll run out of attempts and then get blocked. So you don't want that to happen. Don't enable that feature. Yep. And you have a set of questions?
There is one question about uploading. Okay, so there's documented. So can you advise how to upload data to Scratch for analysis that is over 30 days old? It's on your computer. It's over 30 days old.
So the timestamp, I should say, is only for files that exist on Scratch. So once a file is on Scratch and is untouched on Scratch for 30 days, it is purged. Doesn't matter how old the data is actually, it's just how old it's lived on Scratch and untouched on Scratch. Oh yeah. But
So that's a technical. We have documented options in our documentation, and
yes.
There are some options that do not keep the original timestamp.
Yes.
And so
if you need that file to maintain its date, modification date, and the creation date, etc., then yes, there are options to do that. But remember as well that the 30 days is kind of hard limits. So if you're wanting to get data after 30 days and it hasn't been touched, it will be gone. You'll just have to make sure that you maintain this. And so good policy is, so where would we move file to a permanent storage? So permanent storage could be obviously your own compute resources like your laptop. Pawsey does not provide any permanent storage. That has to be provided outside of Pawsey. So possibly by the research group you're working with, they may have hard drives to save stuff to. If there's a Google Drive or Dropbox that they pay for access for storage, that could be another semi-permanent position. But the idea is that this only applies to Scratch. The purge policy is for Scratch. There's another file system that you saw briefly called /group, and that /group has a much longer purge policy in the sense that it's meant to be for the lifetime of the project. So if you need to move internally for analysis, and you can't get to that analysis right away. So let's say you produced a bunch of data on Scratch and you want to then keep it alive for 60 days because you know you won't get back to it in 60 days, then move it to /group where it can sit for a while. It can sit for the lifetime of the project. There are more strict limits on the amount that you can have access to. So Scratch, half a petabyte of data is kind of not an issue. If you wanted half a petabyte to be reserved on /group, which has got a longer purge policy, that requires requests for access to that type of allocation of storage. And in fact, there's also documentation on how to ask for managed storage as well. So hopefully that answers people's questions about the policies. And I mean, definitely. So here's an example where the backing up, right? So they have a cure copy and they're pulling from /group, courses 01, and they're trying to save some data. So here, group, as I said, has a longer policy. Now, I should preface as well, for the training purposes, the stuff will vanish after 3 days. So everything that you've got on your directories under like COU, XXX number wise, that's going to be gone soon. Right, 3 days it'll live and then it's gone. So don't put anything critical now. Wait till you actually have access as a formal account on Magnus for more permanent copies. Okay, so and as I said, I mentioned briefly, one of the reasons why you want to maybe think about not just doing an SCP command, especially if it's large amounts of data, it could be just the size of the data. So we have these data mover nodes in a copy queue, a partition that happens to exist on the cluster, the Zeus cluster. That copy queue essentially runs in background a job that will transfer data from somewhere to somewhere else. And so that's useful, especially if you have large amounts of stuff to transfer and you don't want to sit there and waiting and so on. And you have let's say, transfer it to from one site that is always active to another site that's always active. So if you're moving from somewhere outside of Pawsey inwards or moving somewhere inside of Pawsey outwards, the copy queue is a very good way of copying data. And it happens to be on Zeus. So one thing that people, if they want to try these type of copy commands, and we can go through it, if you submit a request on, let's say you log into Topaz and you submit a copy queue request that happens to be, the partition happens to be on Zeus, and then run SQ, you're like, you don't see it. So I will show an example of this, but I'll kind of show not necessarily with the copy queue, but with just queuing systems. You have to make sure you specify the cluster you're looking at. So that's a brief overview of transferring data, and it is, as I said, for the most part, it is. There's lots of documentation and lots of ways of doing it. The main thing to keep in your head is that I can do SCP command line stuff. I can use a graphical program, and I can actually log into the system and set up a bash script that says to the copy queue, I want to copy something. Maybe it takes 17 hours. So you put in a request for the copy, make sure that the bash script is set up to copy and move data somewhere else. And then it will start moving that data at some point when it's available. And typically copy queue stuff runs pretty quickly because usually the resources are available. I will pause here briefly to see if there are any other questions related to moving data that anybody has raised that we want to make sure we record and discuss. All good? Okay. Running jobs. So this is where we've briefly talked about this, right? Accessing compute nodes via the scheduler. So running jobs, right? You could technically, in some particular environment, some supercomputers, maybe log into a specific node, look, and then go to that node, and then maybe try to run on that node. But that's one that's not accepted typically, and that's also usually poor practice because you would just get access to one node, and there'll be other things running on it. You never want to do that. You want to access all compute resources via the scheduler, because the scheduler will figure out where the best to place it to make use of the maximum resources and when it can run. And the scheduler and SLURM provide an interface for doing essentially multi-node compute. So if you think of a node, as Christian said, as sort of one computer, the computer is connected via fast interconnect to another computer. And then to make use of that fast interconnect, you really should be running through the scheduler and srun, because they provide all the hooks to make use of that fast interconnect. Otherwise, you might be communicating very slowly. Now, before I kind of show some requests for resources and running jobs, I'm going to just do a very quick aside. This will be discussed in more detail later on about parallel programming. There's different types of parallel programming, and the reason I mentioned it here is because it kind of impacts the resources you would try to request and how you might run a job. So I'm going to highlight three different things because they have sort of three different types of parallelism. So one is OpenMP, which is open multiprocessing. And this is meant to be for shared memory. So there's thread parallelism at shared memory CPUs. So if you have CPUs or cores that share the same physical memory, they can access it physically through essentially on the motherboard RAM, right, on the RAM, there you can run OpenMP parallelism. This cannot do, you wouldn't use this parallelism to span different nodes. It is essentially confined to one node, all right, because it's a shared memory type of parallelism. Across nodes, so distributed memory, where memory is physically located across a different chip. So you would actually have to go through an interconnect, an actual fiber connection from one portion of the computing resources to another. These are MPI, message passing interfaces. There are library routines. They exist for C, C++, Fortran, Python, Rust, R, etc. A couple of different languages. And this MPI process, this type of parallelism allows a communication between different computing elements. So it allows communication across essentially physical motherboards where you actually have to go through a different interconnect and communicate information. So that's MPI. And the other one that we'll mention, because I think it will be useful for a decent number of the projects, because they will be running on GPUs, is GPU parallelism, or essentially non-CPU device offloading. So you can access GPUs via Cuda toolkits, via a variety of different things. But the idea is that I have a computing device that is not a general processing unit, a CPU. And that requires also active thought of the resources you're going to request and how you would program your program, set up your program to make use of that resource. You can't just necessarily immediately just use GPUs. You have to think about it. And so these are sort of three different types of parallelism. One is heterogeneous, right? So heterogeneous, the type of computing elements are different in GPU. You have GPUs and CPUs in the mix. You have MPI, where CPUs exist across different, if you will, nodes or computers, and then shared within the node. And of course, you can combine all three. So the largest programs typically combine everything together to make use of message passing with thread parallelism with device offloading. They combine all three. All right, so you have hopefully in your head a brief idea of like, there's different ways of accessing the parallelism that's provided by a supercomputing system. It's also remembered that there's accessing software is not as, it isn't just clicking on launching an executable. There's different operating systems. There's also different compilers. We provide also debuggers and profilers to examine code and figure out if there's errors in the code or how to improve the code. There are performed mathematical libraries that exist on our supercomputers, and in general, all supercomputers, that are optimized to make use of hardware and do specific types of computation. So MKL, LAPAC, PNC, these are math libraries, typically dealing with matrices and multiplications and calculating determinants. Parallel programming libraries, MPI and Cuda, and we even also have parallel I/O formats. So HDF5 is an example of a library that allows you to write in parallel, so a bunch of CPUs writing to the same file in parallel fast. Not all the software is visible as you log in. And so how do you access this software? Well, you do it through modules. So the module system is a way of loading and unloading access to software. And you can see these set of commands. So I've got module avail, module list, module load. I'll go to the terminal to show you examples of what we would see on Zeus and Topaz, because there are differences between the two systems. Remember, Topaz is meant to be a GPU-oriented system, and Zeus is essentially only CPUs. So the modules that might be available will be different for the two. And these commands are quite useful, so I suggest we give them a try. Okay, so I'm on Zeus here, and I happen to be, I'm gonna do Topaz. So I'm gonna do an explicit thing. This is something Kristen mentioned, which was to set up an SSH key. I had already set this up. I'm happy to show this later on. It might speed up processes as you do stuff. Okay, so I've got two terminals set up just to kind of highlight things. I'm going to go to home. So if I do a module, let me bring this to the top of the screen. So module, the module command, we can even do well, I'll do modules because it'll be simple. Module avail. This command shows you the modules that are available. So you'll see suddenly this output of a list of names, essentially of software or libraries. You can see things that you might recognize if people are familiar with Python. There's a module that's called NumPy, and that is to provide access to the NumPy library. So here as well on Topaz, there is, for people who are somewhat familiar, but I'll just mention here, Cuda, and these Cuda modules are essentially NVIDIA library modules. They provide access to run stuff on GPUs, compile stuff for GPUs. If I do the same command on Zeus, module avail, it will take a while. And here you have a very different set of modules, but it is still ways of providing access to software. So, and libraries. So the example would be, let's say, for compilers, here's an example of a compiler, GCC. You could then load that module and get access to the GCC compiler, specifically version 8.3. And that is, oops, go on. That is what you see here, module load, module name. And you can even see with the default modules that are automatically loaded the second you log in. So if you log in a fresh thing, you'll see suddenly modules. There's the Pawsey tools. These are things like Pawsey account balance that allow you to look at your account and allocation. SLURM, which is a scheduler. It happens to have loaded a default GCC compiler and a specific architecture on Zeus. So there's different types of architecture on Zeus. If I do the same thing here, you'll see on Topaz, again, there's Pawsey tools and SLURM. There happens to be a GCC compiler loaded with a different version, but there's another module that specifies the essentially CPU architecture, and then here it happens to be a different one, Cascade Lake. So that module list command shows you what's available. So now if I do a module load, and I can just do something, we can just try module load GROMACS, because you can see at the top of the screen there was GROMACS, there was one listed, and now we can do module list. And you can suddenly see that there's a few different things that have changed, and that's because the module is meant to provide essentially access to not just the software, but if it depends on any other bits of software or libraries, it loads those modules as well. So this GROMACS one has loaded Go and Singularity, a couple of different modules. And you might be confusing, well, what is an actual module? Well, we can go module what is, and we ask, let's say SLURM. This one doesn't have any information, so it's very useful to kind of see that sometimes something isn't set up. Here, module Go, principally because module SLURM is always loaded, you want to run through the scheduler. But here's an example where Go tells you, you can ask what the module is, and it says, well, it's providing an open source programming language, it's providing a compiler, and it was compiled with GCC 4.8. What about GROMACS? GROMACS edits the path to use the GROMACS tool tag 222. So here, it's a simple, brief summary of what goes on. If you want to swap,
sorry, Pascal, you may want to use the show command as well.
Yeah, I will. So let's do module show, which is a little more informative. And this gives you better insight to what is happening with a module. It sets some environment paths. So here it updates the executable path to include this directory so that you can then run executables. I think I can go to Zeus. I'll just see here. Well, we can just do module avail, and I can ask if there's a module go, and there's a module go, and I can go, okay, what is here on Zeus? Oh, it looks like it's the same thing, and I can also do module show go, and it will show what Go is actually setting. So Go is actually setting a bunch of different paths. These paths then provide access to the Go compiler. So I can now type to object query. I can even look at this particular path if people are interested and see what's there. So there's Go. There's that compiler there. So if I then, you notice here, if I do try to do Go and type it, nothing happens, right? It says that command is not found. But that's because I haven't loaded the module. Now I have access to this command. I can also unload this and then type the same command again. It's like, I don't know what that is anymore because it's unset that path to that executable. So you no longer have access to that particular bit of software or that library. The swap command, which is listed here at the bottom, one of the bottoms, swaps a loaded module with another, but the idea usually you're swapping between related modules. So I would do module, so if I do module list, I might go, oh, I've got GCC here. I go, oh, okay, well, I want a different GCC. So let's look at module avail and see if there are any GCCs. Oh, there's a few of them. Now, the idea here is the best practice is to swap GCC. And I can obviously be explicit, but I don't have to be because this is a current loaded GCC and I can go GCC and I want a specific one. And now you can see it's changed. So if I type GCC version 8.3, if I undo my swap, so let's go back. You can see now it's 4.85. So it's swapping. Typically, the idea of swap is you're swapping a module that's meant to provide the same type of functionality with another module that might be different. So you'll still have normally the same interface. So hopefully this idea of the swap command is that you'll have the same command. So if we had two different versions of Go, the Golang compiler, you could swap different versions. And so have a play, you can see that one, I will just quickly do this now. So if I do module load Cuda here and do module list, if somebody notice there's a Cuda library, but that module is not available on Zeus. Oh no, it is, sorry. It was a GPU cluster. It's not that useful anymore because it doesn't have any GPUs, but it did have GPUs before. But there's not equivalence of modules everywhere. So if you ran a bit of code on, let's say, Zeus with a bunch of module loads and have that translate, I think that it will translate immediately to Topaz, you may need to look to see if the same versions are available or even if the module is not available on Topaz, because the focus of the two clusters is slightly different. I will show Christian's got a question.
A quick question about what does D and LD between parentheses in the module list output refer to? So it basically refers to the modules that are loaded by default.
Oh yes, yes.
So
D is default and L is loaded. So if I go here, let's do Cuda, right? I've loaded Cuda, so it's loaded. There's the L, and it's the default one. So the idea would be, I would always suggest it to be explicit, but if I'll just do unload Cuda, let's do module avail, you can see it's now just got a D. If you don't type a version, that whichever one has the D, if there are multiple versions of the same module with different version tags though, right? It's the same Cuda, but different version tags, there'll be one that's default and you don't have to type the version, it will load that one. But my suggestion is to always be explicit and always be like, oh, I want definitely 11.1. I want to load. And then if I do module avail Cuda, you'll see that the L is now on 11.1, D is still on 10.1. Another question, yes?
I think a very important one. Is it possible to access a version of a module not in the list?
So if the module is not on the list, I mean, there's no module present, you will require that you can update the module path. So the module environment looks in specific paths for module files that then provide environment variables and everything else. But if it's not on the list, it does require either that you have your own version of that software or build a module that provides access to that software. I'll just do this here. Path, this environment variable that happens to be here, you can see it lists a bunch of directories. This is where the module environment on Topaz is going to search for module files. So I might go into opt module files, and you can see there's stuff in SLURM, and there's a bunch of different module files of SLURM. It'll look for modules in this directory. If a module is not present anywhere, it just means that we don't provide that. I mean, typically, if the module is not available, it would require that you either develop, port the software, compile the software on the computer for access for yourself, for the group. And if you want, you can also produce your own module file. We have tools to do software install, like someone can put that into the chat. But if a module is not present, it's typically that we will assist, but we will not necessarily do it for you because the modules we provide are the ones that Pawsey supports. And going forward, it will be important to realize as well. So both Zeus and Topaz have compilers like GCC, Intel listed as compilers. So these are compilers, the Intel compiler, the GCC compiler. So if I do it here as well, avail GCC, so Intel. Oops, not module Intel, module avail Intel. You can see these compilers. I'm gonna, oh, sorry, I don't want to do it. I want to do it in my, I'm going to access Magnus, my own account, because I do want to show that there's a slight difference in Magnus. So if I do module avail GCC, there are GCC compilers on Magnus. This is the big supercomputer that we have. But the idea for Magnus and Cray environments is that you don't access compilers directly. So for people who are needing to build their own code or use specific libraries of the code, for Magnus, it's a different type of thing. You have a programming environment. So module show. We have these environments called programming environments, so PRG, ENV, and there's a few of them. So we can do module avail. I'll just do module avail because I'll show you where they are. There happens to be 3 different programming environments. 3 different types. There's Cray, GNU, and Intel. And this is how on Cray systems you actually switch from different compilers. So you would actually not do program, let's say swap GCC with Intel. You would do programming environments on Magnus. You would do module swap programming environment Cray with programming environment Intel to access a different compiler and a different set of libraries. And that's what's listed in this table here. They have compiler modules, but they're not they don't have the same naming convention or exactly the same structure as they do on Zeus and Topaz. So we've done some examples on Zeus, right? I suggest that you give this a try and see if you run into any issues of swapping the compilers, loading modules. And I would try both on Topaz and Zeus. And so I'll give a minute here. I'll wait for a minute or two so you guys can try the commands yourself. But feel free to ask questions while we let people have a go at trying the module commands.
I just wanted to add that the reason behind modules is because we install software in non-default locations because we want to have several versions of the same software. So you cannot install the software or the software under /user bin because then you can only have one version of each software. So we install in different locations, but the OS cannot find the software without hints. And modules provide a nice way to provide hints to the OS where to find the software.
Yeah. So I'll give a quick example as people are playing this. So if I do module load, I've already got Cuda. So if I see what Cuda can provide, right? So let's just do Cuda for now, right? It'll show me the path. I could then look at these paths and go, what is actually provided here? And so look in the binary directory and you'll be like, okay, this is the executables that I can run, that I get given access to, right? So you can see these naming conventions here, Cuda, memcheck, etc. My module swap Cuda with, let's say, so now I have different versions. Is it 2? 4.2, there we are. So now I can do the same thing. I can, I'll just show again, so we can do the module show Cuda. And there's a different directory now for where the executables live, right? It's now not 11.1, it's 11.4.2, but as Christian said, if you tried to have these, they would have to have different names. They're all the same name, but just a different path. And so this is an easy way of quickly changing the paths in which you're looking for executables that have the same name. It makes it easier for you to swap, unload, and load, and not have to worry about trying to deal with very complicated names. So you don't have to necessarily remember if I wanted this NVCC versus accessing this NVCC, right? So now you can see different compiler names, right? So it's the same compiler, the version is slightly different here. I've got build Cuda 11.1. On top, I've got build Cuda 11.4. Instead of having to do all of this explicit path to an executable, you can just type NVCC and then just module swap Cuda. Oops. Yep, there we are. And suddenly it's much more manageable. So that's the reason behind this module setup. How are people doing with modules?
They were thinking that they can slap between the clusters on the same terminal. So
I've got two terminals open with
yeah,
a login, two different things. So I just happened to log in twice. I actually have 3 logins, right? To show you, I've logged in separately. One terminal in Magnus, another terminal is Topaz, and another terminal is Zeus. So I can swap between the different clusters to kind of emphasize differences. So here, in case you're wondering, so sinfo, right? You could specify a cluster name. It could be like Zeus, Magnus, right? And look at the SLURM, where SLURM can pull different clusters. That's not possible with module. Module is focused on one cluster. And so you can't view the modules that live on another cluster from like on a remote cluster from your own different cluster. That's not possible. Okay, so I might move on, but I'm happy to kind of go back as we'll use modules continuously. So if you've missed a few things, don't worry. We're going to reinforce this as well because we'll use modules as we're going forward. So I have mentioned that there's slight differences on Magnus where you have these programming environments. These programming environments provide wrappers to all the compilers. So the C, C++ compilers all have the same name because on the Magnus, for people who are going to be using Magnus, they have wrappers that kind of identify an alias something. So here I should show, so here I'll just do module list again. I have GCC here, so I have the GCC compiler, right? The GNU Pawsey and C++ compiler that allows me to build codes from source and then execute them. Essentially, it provides the executables. If I then module swap GCC and type GCC, I still always have access to a system GCC. But now if I do Intel or ICC, I have access to the Intel compiler. And on Zeus and Topaz, these programs that would generate executables from source code have different names. So you go from CCC to ICC to build stuff. Whereas in Magnus, the C compiler is always is this wrapper. It's always called CC, no matter what actual real compiler using. It provides sort of a front end or an alias, if you will, to access compilers that are essentially Intel or Cray or GCC. And these are different ways of building the executables. There is also optimized libraries, as we mentioned. We do provide a set of optimized math libraries for building code. So there's like fast Fourier transforms or linear algebra through Cray FFT and Cray libsci. On Topaz, obviously, I did mention that Topaz is particular with having lots of CUDA, so lots of NVIDIA CUDA libraries that allow you to access and make use of GPUs. So you can see there are other exercises to kind of try available, see what HTF5 is, and see what happens when you look at HTF5. So I'm going to do this on Zeus because it's kind of useful to see. And I can go module list just to see what I have. So I have this as my default HTF5. You saw it briefly as we go along. So HTF5, it's got paths. So here's this path, Pawsey, Sandy Bridge, Intel. I happen to be using the intercompiler, right? HTF5, something else. Now, if I swap back to GCC, and I show HTF5, suddenly that path is different. And it's because the module system has updated the fact that the path points to the compiler and that's dynamic. So if you switch compilers, it will point, if that module is available for that compiler, it will automatically update the HTF5. So if I do which H5 dump, which is one of the HTF5 utilities. Oh, here we are. I don't know why it's not there. So let's module load again, HC5. There you go. So you can see the paths updated, but I want to make sure that I really reloaded all the paths and reset stuff so that it's the first instance of H5 dump that's found. And now it's pointing to a different H5 dump. This command, right? So this command is now pointing to a different path, normally the same executable, but built with a different compiler. Okay, so I will briefly mention containers. I would love to go into this in more detail, but it's quite a complicated, well, it's not a complicated topic, it's just a topic that takes a while to go through. So containers, we've mentioned modules are the kind of way of providing access to software. And some people did ask, well, what happens if that module is not available? And one of the paths that we provide at Pawsey is the use of containers. So containers provide a standard unit of software that essentially takes a code and all the dependencies, all the libraries it has, and puts it in a little box that that can be used to generate an instance of that software. And that's called a container, and it's reliable. It essentially provides a reproducible executable. It has operating system level virtualization, but the idea is that if particular packages module is not available, and I can think of a few where we do provide containers for. Example, Alexis, if you are ever running, if any of your projects are run OpenFOAM, the OpenFOAM modules we provide essentially are OpenFOAM containers. We don't necessarily provide the raw software itself. We provide OpenFOAM through containers to kind of encapsulate all the dependencies and make it a bit more manageable to use. And we run these containers with Singularity. So I mention this here because I know that some projects will have to make use of containers. And so just to emphasize that Pawsey does provide support. We've got documentation on containers, on container use, and how to make use of this software in this fashion. Okay, so that's the software access. You've now launching programs. You've already done one, right? So you've had Christian introduce you to essentially running the host name. So that's SLURM executable, which allows you to do a bash script, but you can also do stuff immediately. Run srun. It'll essentially put in a request for compute resources and then try running executable. So on Zeus, through our allocation, I can run srun. I can try to run ls. And if I don't write anything, it's essentially a very naive 1 CPU, 1 core request to run the command ls, right? And so I could do hostname. So we can do this, Zeus1, srun. Now this depends on where this is running. So suddenly you see there's a change. Hostname running on login gave me back Zeus1, srun hostname gave me back a different hostname because it essentially got put on a compute node and run there. I can actually provide arguments to srun to put in lots of requests for resources. But you can see if I ask for help, srun can have a lot of extra arguments. So typically the advice is to not use srun because then you'd have to remember what you provided at the command line. And also that putting in a full resource request is a bit verbose. But you can, of course, do srun and I ask for 1 node, 2 tasks, ls. It will then run on 1 node, but it will run essentially 2 tasks, and the task it's running is ls. And so it ran 2 versions of ls. I could run 28. I get 28 foos. That's the file that happens to be in my directory. If I do hostname, it's all the same host name because I'm asking for 1 node. If I ask for all 5 nodes, which we have access to through our reservation, all of a sudden I'm running on a bunch of different nodes. And it's split up the 28 tasks as best as I can on 5 nodes. So you can see 86, 87, 88, 89, and 90. It's all running there. So this is a way of running parallel jobs. So if you had something that would be, software, you could put in whatever you want and it would run it in parallel. srun is a way of doing this. You can see the normal thing we have here, number of nodes, number of tasks. You can even put a request for GPUs. But these are the best approach is to do bash scripts. So in case anybody hasn't done it yet, my suggestion is that you grab the repository that we provided. Has anybody not grabbed this repository? If not, my suggestion is to put and if you've had difficulty, just put in the chat window and then someone can help you get through and grab the repository. Now, let's try running a single core job. So I kind of did that already, right, with LS. So list is essentially not a multi-threaded executable. It runs on a single core, and it's completely serial, right? It doesn't try to do anything parallel. We can try running on Zeus and on Topaz single core jobs. I would point out that going forward, when you get access to Magnus, don't run single core jobs on Magnus, because essentially you get access on Magnus. There's no shared resource on Magnus. So you get a node. If you run it with one core on that node, you're still given all 24, and you're charged for all 24 on Magnus, even if you run just with one core. Whereas on Zeus, it allows you to share nodes. You can put in a request for one core. It will give you access essentially to one core on one node, and someone else can get access to the same node but run on different cores. It's a shared resource. That's in part why we are running our training on Zeus, so you guys can all share resources. So there is a serial Python code in our repository. So we'll go to, I just saved it as something else. Zeus, this happens to be the repository. You can see hello serial. So if I go into hello serial, this directory contains a script. The one that we want to focus on is hello serial SLURM. Quick thing you'll note that the reservation that is listed there is not the correct one for training right now. It's not course, it's interns queue. And this is requesting a single node, single core, single task, and running Python. It just happens to be running this hello serial Python code, which just prints something, right? You can submit this. My suggestion is you try submitting and then see what happens in terms of resource request. The code as well, you'll notice here, I am not doing the launch through srun. So if I look at this line here, launch, I've just got Python 3 hello serial. If I really want to make use of the compute resources available and make use of multi-threaded, et cetera, then you want to run srun Python serial. So let's, I will edit, people can edit it along. And we can run. Now it doesn't really matter for srun if it's serial code. It's serial code. Well, we can then submit this. Sorry, I've got that little window in front of me. I can then look at the queue. It's already run. There's a SLURM output. It's got hello world. So that is the resource request for running serial jobs. And remember that if you're running serial jobs, you really want to run on Zeus. Other systems are not really set up to be the best way of doing this. There's also suggestions of trying to not run serial jobs. So we've got different ways of collecting serial jobs like job arrays and multiprog. There's documentation on that. I'm happy to go through that idea, but the breakdown you've seen is a resource request, loading modules, and then running something. Okay, so MPI, so this is shared access. So if I then go to hello world, OpenMP, you can see now suddenly there's makefiles. So this is required to make the code. There's a source code. This happens to be the source code. It's a C program. It's a C program that makes use of OpenMP parallelism. There is a couple of SLURM scripts that you can look at where you have a resource request. You can see now task per node is still 1, right? So this is an MPI request, but we're not running an MPI code. So we still want essentially 1 MPI rank, but MPI rank is going to spawn then 28 processes or OpenMP processes. And so you should get actually a multiple set of output as you go along. And if you change this request, then you'll see different numbers. So you can try playing with this particular code. Let's go SLURM. So here, I'm going to be explicit. I'm going to, by default, GCC is kind of loaded, but we should try to be explicit. So module load GCC, you could do swap to make sure you always have some particular GCC. We could want to make sure that we can run it. So we want to do interns. All of this OpenMP environment variables, you hopefully might touch on in some the later talks about parallel, like actual parallel programming. But you can see I'm running something, and I'm running this -n is just saying run on one node and run with this many cores. But if I actually take this away, srun will default to whatever the resource request is above. You won't have to necessarily specify it, but you can always specify if you're going to be explicit and you also want the imprint to be different. And here I can see what I've got listed, and I've got GCC, and let's do module, well, I can leave it there. And we can make, you're like, oh, didn't make code. So I don't know how many people are familiar with compiling code, because this does require compiling some code, but you can specify a file and it will now make the code. So now I have an executable, this hello GCC, and I can try running it on the login node, right? And suddenly you're like, oh, it runs on the login node. And it looks like it's running in parallel on the login node. And that's because there's shared parallelism. So shared memory, you can run in parallel on the login node. And at least this particular code is very lightweight, right? It's just printing something. But the idea is, of course, is to do this in srun. So you could be, I ran it on the login node. I could run this on an arbitrary node, and you'll notice something different. Suddenly, srun, I went from login node providing lots of parallelism, like I suddenly had lots of threads running, and then srun suddenly just one thread. That's because srun is defaulting to one thread. If I then spent 5, I suddenly get 5 threads, and then I can always submit the script. GCC. I can look at the queue. It's running. It's finished. Is there a SLURM output? There is a SLURM output. The SLURM output, by the way, is always typically, not always, but it's typically SLURM dash and the job ID. So you can see I've got the job ID here when I looked at my queue. That's also the file, part of the file name. And that suddenly has exactly what happened when I was running, and suddenly there are 28 processes. 28 threads running in total, as you can see here, and each thread ran. And it ran on a compute node in this case, not the login node. I'm going to pause briefly here because I know that I've also introduced compiling codes and a new type of parallelism. Does anybody have any questions? I'm happy to wait.
So I guess there was a good question about about the file system and about being visible to all compute nodes. I think more in general, it's important to say that compute nodes in the same partition look the same.
Yes.
It makes it easier to program than to run jobs.
So a partition does not need to be homogeneous in terms of compute resources, but it's much easier to manage if they're homogeneous in terms of the resource request, in terms of nodes. If you had wildly varying nodes, it's much harder for I mean, you would also get maybe poor use of some nodes if they suddenly had, if one node had 66 threads and the other 66 cores and another had 22, SLURM would know, but suddenly you would probably maybe access only 22 of the 66. because it's in the same partition. So it's much easier to manage if they're homogeneous.
Can I ask a question quickly?
Yep.
So just about like a keyboard shortcut, I think you're doing. Sometimes you're typing out like half of a file name and then looking like you're doing some sort of keyboard shortcut to show you all of the possible completions of what you've already written. So I know,
Yes.
you know how you can like tab complete something.
Yes.
Yeah, but it looks like you're doing something else where it shows you like all the possible.
So if I do tab twice, so if there's a multiple set of possibilities.
Oh, right.
If
If you tab twice, it keeps what
tab,
you've already written.
And it's just like, okay, well, everything that starts with mod is this that you have access to.
Right.
And then if it gets to the point where there's only one unique, it'll just complete. So
yeah.
module, there's nothing else that goes, tab completes.
Yeah. Okay. And when you say threads, is that number of nodes?
No. So threads is essentially per core process. You can. It's a bit of a funny thing. So on a CPU, right, you have multiple cores, essentially multiple computing units.
Yeah.
Each computing unit effectively can run one thread at a time or one process at a time.
Right.
The terminology is usually a thread is and a process are not quite interchangeable, but very much mapping. Like you're running a particular set of instructions, and that would be one thread running a particular set of instructions.
Okay.
A node so the idea is that one is just about like running instructions. So how their instructions are run and how things are managed could be hardware specific, because you can run with many threads on a single physical computing unit. What happens is that one thread will take precedence, do its set of instructions, then another thread will come and go, well, now I can run my instructions. So you're kind of waiting. So I think briefly it was asked in the chat about a SLURM thing, which has processes per CPU. And typically you want to, I mentioned this as well, so it's a good question. You typically want to make sure that you have essentially one set of instructions to run per core, because the core can't handle multiple instructions fully. There is something called hyperthreading where you can run instructions that are purely logical instructions, like an AND or an OR. You can run two at once, because typically a lot of computing units have two logical essentially units in the computing infrastructure. They can run two logical instructions completely independently at the same time. But a floating point operation, there's only one per physical core, essentially. There's one floating point set of instructions you can kind of run. The threads are sort of a higher level there, set of instructions you want to run. And then nodes are an amalgamation of hardware. So you have a bunch of RAM and CPUs with maybe multiple cores, and that consists of a node.
Okay. All right. Thank you. So nodes don't necessarily contain multiple cores. Not necessarily. If you had some very, very old supercomputers, right, that might have had one, like the first supercomputers would have had multiple nodes, but per node there would have been one CPU, and that CPU would have only had one core, right? If you go back way back in the day, some older computers. Yeah.
Now they're essentially, if a CPU is provided, all the CPUs that are essentially constructed right now are all multi-core. They all have essentially multiple compute units. And nodes typically are dual sockets. So they usually have like two physical CPUs that have multiple cores that can do computing.
Right. Okay. Thank you.
Okay. So I'm happy to do the MPI example. And so I kind of did it as well. So let's go through the MPI example. So this is going to be across nodes. It's not going to be shared. You can do it on one node, but you can do it across nodes. So let's go hello MPI. Okay. So we can make. Let's do this on Topaz. So I'm just going to switch up because it'll. So I'll go into my Scratch. Same thing, right? Remember, I've got access to the same Scratch. Yes.
So while you do that, I'll answer a couple of questions on live. So the difference between SRAN and SPatch, because you use the SRAN to launch some application directly. So well, SPatch submits jobs for later execution. It puts the job in a queue, whereas SRAN waits for resources to be available to execute the job.
Yeah.
And so SRAN is used within batch scripts when the resources are already available. because the job at that point had already waited in the queue, has already waited in the queue for the resources, and when SLURM executes, it has the resources allocated. If you run SLURM on the login node, then I believe Pascal can confirm, but it would hang if resources are not available.
Yeah.
And the other question is, if we specify an impossible configuration, for example, CPUs per task, 1,000 or 100,000, it does not
Doing that now.
exist.
Yeah.
It would fail the job execution because it cannot be satisfied.
Oh, forgot. I need to alter this. So I'm just going to take this away. So let me show. So I'm gonna. Where? Oh, sorry. I need to add a. So I'm going to do the MPI example. Oh.
So sometimes the issue is that these examples have been written a couple of months ago, and we update software, and sometimes you need to update your scripts and you have to update your workflow because maybe the software that was used at the time was not available anymore. It's been removed because deprecated or something. So sometimes you need to brush up the scripts.
Yeah, so that's. So I'm going to be, so I'm in that request, right? So I'm running MPI. I'm asking for 1,000 MPI per node, right? So I want to run 1,000 MPI job, but Topaz.
I would actually be careful on the terminology. You would run tasks, MPI tasks. MPI jobs is different.
Yeah,
because it's
MPI,
quite confusing using all these terms. At this point, I would take the option to differentiate between process and tasks.
Yeah.
So I don't know if you want to do that, Pascal, or I can do that.
Well, so for MPI, for SLURM, it's very common to write task. There's lots of echo, Christian. Oh no, it's gone. It's gone. So MPI tasks. So MPI is this message passing interface that essentially spawns effectively the executable a bunch of different times. So if you ask MPI run, I've got this example I can do because I've got MPI loaded. I can ask for 10 LSs. So I'm listing it 10 times. MPI, what it does is it will take that and go, I'm going to take 10 LS commands and run them. And for MPI code, what happens is usually that there's also communication between these instances that are running. So they can kind of communicate with each other. But each MPI task is given essentially an executable to run, and it will then run it. And if there's no communication between MPI tasks, like an embarrassingly parallel problem, you essentially get what I've got as this output, which is LS, which is not, LS is a command that's not parallel, it's not MPI aware, it's completely independent. So essentially it's as if you're doing LS 10 times and you get the results 10 times. If you're running commands that know about MPI, then you can get some communication between the MPI tasks. The MPI task can then start running different processes. So an MPI task can then go, okay, I've got, let's say, 7 different instructions to do. I can then spawn 7 different processes to run those instructions if they're independent or if they're dependent. And that is the difference in even in SLURM, it's replicated here. The term is old, it's kind of bad. So tasks is essentially MPI related. CPUs is not CPU related, it is CPU core related. So before this, the CPUs only had essentially one computing unit, one core. There was a direct mapping between the number of CPUs you're requesting and the number of cores you could run, like the number of supercomputing instructions you can run, processes you can run. But now that's not the case. So this is best, even though the terminology is stuck, it's not CPUs. You're not asking for a CPU, you're asking for a CPU core. And here, the terminology you can see in SBatch is very specific. I'm asking for one node. I'm asking for 100 MPI tasks, and each MPI task I'm saying I'm going to give you access to essentially one CPU core on which to run the instructions you're going to do. And I could change this where I could ask for 10 tasks per MPI, and then per MPI I'm asking 100 MPI tasks. So and that means that I need, in terms of computing resources, 1,000 cores, right? So this would be a large request. Now, if I try running this, you can see bad job submission, more processor than permitted. I cannot actually request this type of thing. This is not available to me. And so at least on Topaz and Zeus, the footprints are different. If I then start going down and go, let's ask for one task, one MPI task, 10 CPUs per task. So this was kind of similar to the OpenMP request. And then do SLURM. You can see it's accepted. It will run. But what's interesting, hello MPI. No, I have to make that. I forgot to compile. Sorry. Okay, let's submit that again. Oh, sorry, that's a shortcut for me. Doesn't happen on this account. So now I've got this output, and you'll notice I asked for a lot of cores, but I only asked for one MPI task. So I only see one MPI rank running. So there's a 0 and 1. So the total number of MPI tasks running is 1, and it's rank 0 of 1. If I then change my request so that it's more in keeping with running MPI, so if I'm running a pure MPI task, I want to put my parallelism here and not in the CPUs per task. And we can go. And here suddenly you can see that there's parallelism happening. I can see that there are 10 MPI tasks that are running with the ranks from 0 to 9, and they're all just printing hello world. And so that's why you kind of need to know to some extent what parallelism is implemented in the software you're going to run, because the resource request will impact that, right? If you're running a shared memory program and you ask for a bunch of MPI tasks, you basically get that executable running 10 times without the parallelism that's really implied in the executable. So it's not effective. It's actually, you're kind of wasting resources. And if it's MPI and you're asking for lots of cores, but lots of cores per task being something and task being 1, then you don't get the parallelism you're expecting. Okay, so, oops, all right. Yeah, so the other thing that to go through is GPUs. Now, the GPU request that we've gotten, the executable, remember that the GPUs are only available on Topaz. So if you tried running this on Zeus and put in a request, there are no GPUs available. It will not accept this request. And so the GPU parallelism is a little harder to see. So if we go into the vector add directory, so this directory has 2 codes, as it were. You can see a CPU vector add. This is meant to do essentially all the compute on the CPU. And then there's the equivalent GPU code. And here, the compute is being done on the GPU. So essentially, there's allocations for saying to the CPU, talk to the GPU. So you can see there's a lot more code involved here. There's these commands called Cuda check error, like Cuda malloc. It's essentially a way of talking the CPU, providing instructions to the GPU on how much memory to allocate, and what instructions to run, and how to talk back to each other. So you essentially have to have some method of in the code of talking between the two. So if you do any development, that will be involved. If I look at the script, here you can see the script is going to run on, it happens to run on Topaz. It's got a very specific request. Here it's got the GPU, essentially device request, asking for GPU and only one of them, and then running. Now, if you run the CPU code and the GPU code, what you'll notice is a difference in the amount of time taken to do the compute, and not necessarily immediately obvious a big change in the output, because the output is meant to be just providing a quick calculation of essentially a vector add. The other thing as well is that you'll notice, I put it here, right, that there's this loading of GPU enabled code. So you basically have to make sure that you load stuff with the dash GPU if you're on Topaz. This will be important for anybody who's doing GPU stuff on Topaz to do any compute. So if you look at the script again, just look at the script, you can see an srun nvcc code. You actually have to compile on a compute node to make sure you have access to the GPUs you want. So if you compile on the login nodes of Topaz, they don't have a GPU in the, well, so some setups might have on login nodes some GPUs, but typically we do not. And also going forward in Photonics, the login nodes will not have GPUs. So if you want to compile for GPU, you basically compile on a compute node. So you actually do the compilation there. And you'll notice, like the previous things I was doing, I was just typing make in the login node, which is not what you want to do here. So that's why this script is there. And then we can even, let's just update the script, right? So we have this srun add. If you wanted to, you could also then run just a GCC for compilation of the GPU code or the CPU code. So you could add CPU. And then run that code.
So I would suggest to increase maybe the number of elements in the to add to see the actual difference.
Small. But the idea here is that the codes are quite different, and so you have to compile differently. And also, it's not here, but remember that you'll need to add the reservation.
So actually, there is a question or a note. You can compile CUDA code on a login node without the GPU. Not in every case, though. Because if you use the CUDA drivers, those are not actually part of the CUDA installation, and they are only to be found on the compute nodes. So for some codes, you actually need to compile on the compute nodes. In general, as a general practice, we always suggest or recommend to compile codes on the compute nodes in any case. Also because you compile for the specific architecture you are running on. The login nodes may be different from the compute nodes.
Yeah, this is particularly true of Topaz, right? Because even though the NVLink is down, we do have two different types of GPUs in the Topaz partition. They're separate partitions, but on the Topaz cluster. So if you compile it for one and then try to run on the other, there's going to be differences in drivers, and it's going to be an issue. Did you want anything else, Christian?
Not really.
Okay,
that's good.
So we have the script. We can obviously submit this Smash script. So let's see if it actually works. Let's see here. Oops. Okay. Oh, did I type it incorrectly? It is vec add. Oh, not vector add. Okay. So in my SLURM script, at least you can see that the CPU code run, I mistyped the compilation for the GPU, sorry, the CPU code. I'm just going to move it. I would prefer them to have the same naming convention. So vector. Okay, so I've submitted my script with SBatch. I can look to see if stuff is there. And at least currently, the common array. Oops. Did you have, I guess that's a leftover, is that?
Oh, probably it's a leftover. Yeah, there is probably, yeah, it's a leftover.
I might increase the size, as you say, because you might not notice it. So I'm going to increase the size of the compute. Make sure that they're kind of the same. Okay. Keep doing that. I'm so used to it.
So what are you doing?
So I've just essentially updated the code to actually work. So there's some typos in the code. And I also just increased the size of the computing element that was being done. And I will just quickly show that on screen. So for people who are interested, I can do actually, probably be interesting here to see what's going on. So there's updates you need to do. So you'll need to change the script to have a reservation, make sure that reservation is there. Everything else is kind of fine. I've added a compilation to make sure that I've compiled the CPU bit. So the code would have worked, the script would have worked before, minus you need to add the reservation for interns. And that would have essentially produced a result, computed something, reported all good, and that would have been the end of it. And the reason I want to show AR63, let's do this. Print array, terse, implicit function array. Ah, okay, so you still have some leftover stuff in.
I'll try to run the code because I copied this code from a folder I have. I'll try to fix this this one. So meanwhile, Pascal, there is an interesting question about about parallel programming and code. So does using Cuda or MPI directly can make the code parallel or run in parallel, or should we modify our code? So
right. So just providing the, let's say, loading the module MPI and loading module Cuda does not provide parallelism. The code has to have in it the ability to use MPI and to use GPUs. Otherwise, just loading these, essentially the libraries and the compilers that are associated doesn't immediately provide parallelism. So you have to actually look at what the code is, what the code can do. For some people who might be doing some machine learning with TensorFlow and PyTorch, essentially those codes are set up to make use of those resources. So they will look for, but they're already set up. The code has been set up. If your code was set up like the Hello Serial Pi, right? Or even just a Hello Serial world, if it was a C code, you compiled it with MPI and Cuda. So you compiled with MVCC and MPI and everything. Even if you compile, use the compilers that are meant to provide the ability to access parallelism, if there's no parallelism in the code is still serial. It will not use those extra resources. You're just providing the ability to do stuff. So a good example, sorry, I need to exit that. So let's just go back to, is that code CPU vector add? So this is a C code. There's a couple of function calls to init a vector and then add some vectors. And if you look at the vector add, right, it's taking a couple of arrays and just adding it and saving it into another array. So that's the computation that's going on. Now this computation could be parallelized by MPI, OpenMP, and GPU. But as it stands right now, even if you added the ability to do it, the code will not make use of that because it's set up to be only serial. It will not make use of any extra parallelism. If we then go to the GPU code to look at what is necessary, you can see that the code has changed quite drastically. There's a vector add. This is meant to be a kernel run on the GPU that provides specific access to some bits of memory, and there's implied parallelism, or parallelism when you're actually doing the compute. So there is this vector add command here, this is essentially providing the parallelism to run an instruction on the GPU. And that GPU has inherent parallelism because it's got lots of computing units. And so suddenly it will do lots of compute in parallel. But you can see that the code change is not that is actually, rather, it's not complex, but there's lots of things to do to make use of that parallelism. It doesn't suddenly just appear if you load modules.
Yeah, if they're trying to use some other softwares, they should look into the manuals and find out whether the software they're
yeah, you should definitely look at, like, for the example when I was loading a few stuff. So there's module avail. We provide some software, right? So there's software that exists through modules. Some of this software is serial, some of the software is non-serial. So I'm just going to show this up here because it's kind of useful. There's even explicitly what's going on. So here, HCF5, there's a module that says, I'm providing you a library called HCF5, and it happens to use parallelism. There's one that is specifically non-parallel. That library has been compiled, and the code has been set up to make use of parallelism or to turn it off. So one case we turned it on, in another case we turned it off. But you need to look at what software you need to use. So Forge, actually probably FFT, is a good example where you can run this fast Fourier transform library in parallel, in serial mode, in parallel mode. Which one's which. I mean, here we provide all, but you need to look at the software that you're going to use. They should tell you. The read the docs documentation should provide information of how it's running. Okay, so have people played with running a job and looking at output? If you haven't and you're struggling, can you please let us know? Any comments? Okay. So we have gone through non-interactive parallelism. Essentially, like you submit a job, it waits for resources and it runs. Yes, Christian?
So there is a question regarding the SLURM file for the GPU.
Yeah.
Does CPUs per task specify CPU cores or GPU cores?
So the request, let's load this up here.
So essentially, once you request a GPU with the GRES GPU, you request the entire GPU. There is no partitioning of the GPU like there is a partitioning for the CPU, let's say.
Yeah, it is not possible, or it's very non-trivial to try to share compute of a GPU. So you ask for a GPU, you get all of it. If you use one of it, you've gotten access to all of it. It will just run one instruction. So the good example would be, you'll notice the lack of, let's say, speed up of using a GPU. It'll probably be even slower. If you don't use, if your compute uses, like if it did just one add, doing one add on a CPU is much faster than sending the scalars to the GPU, using one portion of the GPU to do one add and then sending it back. So you get all of it. And in terms of all the SBash commands that relate to number of tasks, number of processes, number of threads or CPUs per task, and number of tasks per node, that all relates to CPUs. The GPU request obviously is for the total number of GPUs. So you can ask for more than one GPU. We could do 2.
One important thing that we mentioned here, that GPUs are tied up to the host CPUs.
Yeah.
That's how you reach the GPU through CPU.
Yeah. So you always need to have some CPUs to talk to a GPU, right? And you can see I asked for 2 GPUs and it ran, the job went. But if I then asked for, I don't know, let's ask for 784 GPUs. No, right? There's only 2 per node. And those two GPUs, essentially I mean, we could try to enable this, but it would be very slow to have GPUs talk to a CPU that exists on a different node in terms of, because ideally you want the CPUs that do the most talking to a GPU to be on the same node, on the same motherboard, and you minimize memory communication. You can, of course, do communication across GPUs, across nodes, and across CPU communication across nodes with MPI. But for really fast access to a GPU and memory transfer, you hope the CPU that does the most talking to a GPU is the one that lives closest beside it in memory. Okay, so we can do some interactive allocations as well. So we've done all the stuff. So I want to, I guess, maybe show this. So SRun 5 or 5. I guess it'll run immediately. Let's try 28. Oh, I didn't make it. Sorry, I ran this on Topaz. Let me just make. Oh. Module loading the OpenMPI to make the code, because this is an MPI code, so I need to have access to that module to then compile it. So I've got that code. I've got an executable. I can then run that executable. So let's actually edit the script. It's SLURM, right? And now let me run with 5 nodes. And I'm going to take this away because I want SRun to just follow the full resource request that's in SBatch. Right, so you've seen this type of thing where SBatch, I run then SLURM. What did I do? 5 nodes. Oh, did we get 4? Oh, sorry, 5 interns. So I'm updating the reservation. And I just want to reiterate this to show, okay, so I put in a request. It's then going to run. Sorry, I always have a shortcut that usually I do. It's now running, right? It's running in the background. It will finish at some point. It finishes. I can then look at the output. There's 140 things running at the same time. I can then run srun and put in a similar request by going 5 nodes, 28 tasks, reservation equals interns queue, and the code I want to run is the hello MPI. It helps if I can type. And you can see now this is sitting for a little bit. It sat, that srun sat for a brief moment to try to make sure it could get resources, got resources, and then ran. So if we all do this command, if everybody put in this command at the exact same time, you'd notice you'd wait because someone would get access first. Everybody else would have to wait for that code to run, then get access and run, and so on. Right? There's not an immediate request. I could then, but I don't get to interact with that output, right? I want to interact with something. This is where this command, SLOC, allows you to essentially get access and interact with something. So if you were debugging and you were really interested in debugging code or looking at how things behave, SLOC is a nice way of doing this. So we can do, let's do 2 nodes. Let's do 2 tasks per node. So this is SLOC. Obviously, you're going to have the reservation that I want to use. And then you can see I'm waiting to get those resources. I suddenly have resources, and suddenly I'm back to command prompt. So you can see the difference though, right? So our login node was here. There's Zeus1. And suddenly I'm on Z043. And it's because I've asked for an allocation, an interactive one on the compute resources. So now I'm running interactively on the command line with compute resources. So now I can do make, it's already made. I could run hello world. It's not going to work super well because it's not, it's waiting for some MPI, but I could do srun. And now I don't have to, it'll just run automatically. And you'll notice there's only 2, but it's because I'm running on two different nodes. So if I do host name, you'll see two different host names pop up because I've asked for two different nodes and I've asked for essentially two MPI tasks. That happens to be one MPI task per node. And suddenly I get two different nodes. I'm running actually on two physical different nodes, this command, right? And I can run stuff interactively. I can interact and I could say, oh, this is not what I want. Let's change hello MPI. I wanted to write, I don't like hello world. I want to say, hello everyone. That's the thing I want to do. I could then type make, and then I could run the same thing again. Oops, sorry. And suddenly I have hello everyone. So SLURM provides an interactive means, and it's pretty useful for debugging. If you're debugging and you're kind of going to constantly edit code or constantly do some editing to get somewhere that you're happy with, to then send off a resource request that's larger, this is a very useful thing to use. The command is SLURM. And then you, like srun, SLURM, provide the resources you want, the time you want it for, etc. So I would suggest everybody try an SLURM command and see what you can do as well. So you could try running here srun. They've got an example, interactive sessions running Python serial. You can run a few different commands. The idea is that you'll notice that you'll be given a node. And some people might be even given, if everybody asked for, let's say, everybody try SLURM, two nodes, two tasks, MPI tasks. So this specific command, some of you will be on the same host. But if you looked at the cores you were given access to, some will have different cores. So I'll ask again, I'll see where I am. And can someone type srun hostname? I've been given 43 and 44 again. Is anybody else given 43 and 44? If you have, Joe, okay, cool. Now, so Joe is on there, and I could try updating my request. Yeah, go ahead.
While you were explaining that, I was fixing the GPU code. Actually, I had taken the code out of a repository, but there were dependencies missing. Sorry, Pascal. I've actually been running the code, and I wanted to show the results to the intern people, and I want to quickly share my screen.
Okay, go for it. You should be able to steal my screen.
Yes. Simply what I want to show is that. Okay. Many windows open. So you should be able to see my terminal. So I'm on an interactive session on a compute node with the GPUs. And at this point, what I did is, but first of all, now that you are in interactive session, you can run your compilation commands directly on the terminal, or you can run your programs on the terminal, or you can simply run the same script without submitting it to batch, because at that point, those comments are just comments. And what I did essentially is the same code that Pascal showed, just that with all dependencies there, so it works. And what I did is I just left the commands to compile the code, and compiled the code already. And then what I did is increasing the problem size a bit to 1 billion elements. So we are adding two vectors of 1 billion elements. What I did is first running the GPU command, and I've run it through the profiler as well, so that we can take the exact time of the actual addition, because the code itself will also initialize the vectors, and we also do some cleanup afterwards. Well, what we're really interested is the actual operation of adding elements. And as you can see, this using the profiler is the fastest way for me to show you the actual execution time of the addition itself. and we have only one call to the function, and it runs in 14 milliseconds. So if then what I did is timing the CPU version. Now the CPU version, there is not a the quickest way for me was using the time command. The time command reports 24 seconds. Now, if you consider that there is also the initialization of the two vectors, you can how to say, for simplicity, you can even divide the time in three, evenly between the two initialization of the A and B vectors. And then there is the addition. And even if you divide by 3, then you would get something around 8 seconds. But you have 8 seconds compared to 14 milliseconds. So it's actually a couple of orders magnitude faster the GPU.
Yeah.
And as you can see, once you request during the allocation itself, when I request the interactive allocation, I ask a GPU here. Then when I run my command here, the command is able to see the GPU without any particular command. But this is to be used for this kind of profiling and interactive sessions. Usually you write the script to run your program.
Okay. Do you want to stop sharing?
Yes.
Share? Okay. Okay, so the people have tried interactive sessions, I hope. I feel like they're comfortable a little bit to explore in interactive sessions. Christian showed you a very good use of an interactive session where kind of looking at debugging and profiling codes. So it's quite a useful thing to do. And even in our example, we also make a point of kind of like a lot of times people ask for the debugging queue. So the debugging queue and the GPU debugging queue, these are partitions where you can only request minimal resources, but you're given quick access to those resources so that it's easy to kind of get access. Now, real world use. So we've shown hello worlds of vector add, hello world MPI, hello world OpenMP, and kind of serial. They are normally quite simple examples. That usually the real world is much more complex. You have to do a lot more complicated instructions. But of course, you want to run whatever you're doing as fast as possible. And you want to minimize the wall time within reason to do some compute. So obviously, if you can run something in 14 milliseconds, that's fantastic. In the profile that Kristen showed, they also showed how the mem copy, so copying from the CPU to the GPU, and that was about 7 seconds. And so if your compute on the CPU only took 4 seconds, right? Even though the compute on the GPU took 14 milliseconds, you might be like, well, overall, I still want to use the CPU because it was the mem copy was long enough that I didn't want to do it. It was longer and so on. So there's things to think about as you're going along. So you want to eliminate the wall time, but you also need to think about the cost. So you cannot indefinitely scale code, right? At a certain point, adding another computing element, the example would be, Kristen went to 1 billion, we said, elements. So if you do 2,000 elements, you don't get, if you do 5 elements, you're just not getting any speed up. The GPU is not providing any speed up. It won't scale any faster than doing 1, 10, etc. You really need a large number of elements to notice speed up differences. And there's also a certain point at which you will no longer scale. So if you're doing 1 trillion elements, one, you wouldn't be able to fit it on the GPU memory. But also there's memory bottlenecks. It's also how the code does stuff is like random access order. So if things are randomly accessed all the time, that can be quite inefficient. And so there's only a certain amount of how you can scale. So you do need to think about the costs for the stuff that you guys are going to submit. And it's the wall time times resources. So if you are requesting lots of resources to shrink the wall time, great. But at a certain point, the efficiency of the code will mean that you can't just keep requesting more and more resources. So the and for large jobs, right? You might request it for 100 nodes. That's a lot of compute, and it ends up being about 28,000 core hours for one on Magnus. If you're requesting that, you're using 20,000, 30,000 SUs or service units, and the typical intern program was 10,000, right? As a 50,000 on, exactly. Okay, so on Topaz, if you got 20,000 and the thing you want to try to do took 30, kind of fine, but you're using all your resource in one go. So it might be that, especially if the code is very inefficient at that point, you could regress fewer resources, wait a little longer, and make better use of the allocation you have. Now, I kind of mentioned this as well, but you do need to think of how the codes are doing their parallelism, right? Whether it's distributed memory or shared memory, and just providing the presence of, let's say, the open MPI module. So provide MPI as a module does not mean that you get that parallelism. You have to make, that code has to be able to use that type of parallelism to begin with. Some codes are, best tackled with GPUs. Some codes are best tackled with CPUs. And then, some are embarrassingly parallel. So there's no communication. You're essentially doing let's say that LS that I ran. LS is an embarrassingly parallel program, hitting the server. But if you did something similar where there's no communication required, everything is completely independent, those real world uses that embarrassingly parallel problem can scale indefinitely because there's no communication required other than the initial start point, right? Now, in terms of HPC, as we mentioned in the first instance, the idea of supercomputing systems is that you have a computing unit that provides essentially a motherboard with CPUs, GPUs, high bandwidth like memory, and quick access between all these various elements on a given node, and slightly slower access across nodes. So the fastest thing is in terms of communicating memory, because you're always going to do that. If you're computing something somewhere and then saving it, it's got to go to RAM. So it goes from the RAM to the CPU's cache, then goes back to RAM, etc. That's all on a compute node that's very fast. You then connect these up with very fast interconnect, but there are limitations, right? And there's even limitations that you might say, well, why not just build a RAM chip that's physically larger and has 2 terabytes of memory rather than a bunch of individual RAMs that contain 16 gigs and another 16 gigs, another 16 gigs. Obviously, if you need to replace an element, suddenly you're replacing 2 terabytes versus 16 gigs. So there's just obviously engineering issues, heating issues, and so on. So there's limitations to how much computing you can put with the fastest access in terms of per node. And also there's also issues of communicating across node. You can't have indefinite, 20,000 node computing superclusters because there's cabling and communication latency and so on. So the key thing, of course, to get across is the HPUs are not a simple large CPU or a super fast CPU. There are many CPUs connected together to do compute. So the software has to account for this to do it. And that's where OpenMP, MPI, Cuda comes in, and you have to have these codes that do it. But I wanted to raise this because it's kind of an interesting thing. So we mentioned at the beginning of the introduction, there's a computer called Fugaku that is on the top. It's the fastest computer in terms of the number of floating point operations it can do per second. And it kind of gets close to 1 million teraflops or a billion flops. So that's the gigaflops, right? So because it's close to the exaflop scale, but it's designed to has a fast interconnect and so on. But some programs don't really need that. So folding at home is a good example of an embarrassingly parallel problem. They send off little packets of data on your laptop and you do some compute. And the folding at home, this was a little while ago, but if you looked at what they got available to them as computing resources, they had 3 million CPUs, 250,000 GPUs, and or close to 300,000 GPUs, both AMD and CPU. And the total number of CPU cores, not just CPUs, but like computing elements, was 21 million, right? But it's an embarrassing of a parallel problem. So they were just running on laptops everywhere, right? They didn't need to do the fast communication. So this was exascale level in one software, but it's an embarrassingly parallel software. And that is a very special case. Most of the time we will not have, you'll need to have things talk to each other fast. And an example of protein, so protein folding home is folding proteins, but like very simple calculations. If you want to do really complicated molecular dynamics, you could do something like NWChem, which is a software, and that does need fast communication. It doesn't scale indefinitely. At some point, given a problem size, adding more compute does not do anything. And so because each pore is doing a bit of the simulation volume and then has to communicate the results often and quickly to other cores doing other portions of that simulation problem. So here's a good example of indefinite, so it's sort of inefficiencies that crop in. So here is doing a specific simulation with NWChem and the number of cores that they're adding into the compute to do it, right? So they're doubling every single time, and then the wall time, the decrease in the wall time taken to get results. And then here an example where you increase the computing resources by 2 and you kind of get a wall time shrinkage of 2. But then if you do it again, it doesn't shrink by half. You know, you are getting stuff that's running in less time, right? So here you're looking at 1 hour of compute using 1,000 cores, but then you're getting to, you know, still 0.75 hours of compute and using 4,000 cores. And so it's faster, but it's got much higher cost. So it's not suited to the resources you're providing. And so going forward, you guys will have to get used to the idea of thinking, what do I need to do? Okay, I want to do it in 1 second. Can I? Maybe not. You might have to wait 5 hours. And the 5-hour compute time might be not as good as just waiting 7 hours and using less resources. And you can't just keep pushing the number of cores, right? So there's this turnaround in which you get the relative cost of doing compute. So this is the cost as you increase the number of cores, the relative wall time. So it's dropping nicely. But at a certain point, the inefficiencies of how the computation needs to be done by the software, it means that throwing more resources at it means it's not an efficient use of those resources. And so the efficiency starts, the cost starts increasing. But of course, the idea is to try to increase the scope of your science. So we do want to provide resources. I have a question.
So can you get an estimate of the wall time through experiments runs, essentially?
Yeah, so I will, how to explore. So I'll jump to this right now. So obviously it's very problem dependent and it's not even code dependent. Some codes like the NWChem that I mentioned, some type of simulation volumes will be very efficient in how you can distribute workloads. And so you can throw more resources at it. Other ones are not. And so because it's a priori not obvious what the best decomposition to be resources and wall time, you do have to experiment. So there are people doing scaling tests. Thankfully, for a lot of software that's available, like NWChem, other people have done scaling tests. So you can look at the scaling test and how the code behaves and go, all right, this simulation that they're running is similar to my simulation. It took 17 hours on 1,000 cores. It's probably going to be something similar. But realistically, if you are starting from scratch, not necessarily knowing how stuff scales, and you're kind of going from your desktop, I would use your desktop on small sample problems, see how it scales as you increase the problem complexity. And then when you're migrating to Magnus, Topaz, Zeus, you'll have to do the same type of scaling test where you have a fixed problem size and you throw more resources at it as you gradually increase, let's say, the number of MPI tasks that you provide to the code, right? It's really good to get the idea of the scaling tests. The wall time compute, like the total wall time taken to something is, is very non-trivial. It depends on how far evolved you want to evolve the system. So if you want to do a protein and fold it only once, figure out some folding, maybe that's not that bad. But if you want to see the interaction of a protein with other proteins over 10 nanoseconds, that might take a lot of compute depending on the interactions, and it might take a lot of time. I'd love to provide a more simple arithmetic, like mathematical way of determining the wall time required. The best thing is to start off with 24 because that's the maximum you can have. And if and also to make sure if your code has checkpoints and restarting. So the idea is that there's a lot of codes, as Basha mentioned before, which can run part of the way. So let's say you want to do 10 nanoseconds, and in 24 hours, you can only get to 5 nanoseconds. Some codes offer the ability to essentially go, I'm stopping in an hour, I'm at 23 hours, I'm running for 23 hours, I need to start writing an output so I can restart myself from this save point. So save the output, and then restart again. So that's why the suggestion is ask for the maximum time and see how far you get. Hopefully it's less than 24 hours. If it's more than 24 hours, and this was a question, if it's a lot more than 24 hours and you have checkpoints, so like restarting capability, saving capability, that's fine. But if it's not, that's a serious issue. And it's not a serious issue supercomputing wise, it's a serious issue of getting results wise, because if you need to run for 17 days to get an answer, what if this computer goes down in those 17 days, right? That is not ideal. So hopefully at that point, if it's the 70-day end result time, you can add more resources and shrink that 17 days down to 24 hours or less. And if that is not possible, that does require like thinking about what you're going to do, because it's not trivial now. That's a very, yeah, you have to figure out how to do stuff in steps. But always, same thing with GPUs, when migrating to GPUs, it's a little bit more complicated because it's not obvious to translate a task from a GPU to, from a CPU to GPU. But I'm going to briefly mention that we can explore this if we have a little bit of time. I'm happy to do breakout rooms, but we do have a way of showing how GPUs could be used to speed up compute. We showed the vector addition, but a common thing is TensorFlow and some AI software. TensorFlow is a great example of software that is GPU aware. And so we'll use GPUs if it's available, and we'll severely reduce the compute time necessary. But again, how to explore in terms of how much you can scale, whether 1 GPU or 2 GPU, that's a trickier issue. Again, wall times, starting off with a simple set, understanding how much time it takes to do the simplest basic compute, possibly not on even the supercomputing resources, but then looking at how, as you increase complexity and increase resources, how that behaves. Of course, we are here to help, and as are the mentors who have had some experience using the Pawsey systems, but there's obviously tons of stuff on the Pawsey website in terms of documentation, good knowledge base. There's also support tickets. You can raise a request. If you are going to contact the help desk at Pawsey, it's really informative for us to know like everything about the job, like what modules you use, the error messages, job ID, etc. In all of these things, again, you'll notice the last statement, please never tell us your password. We don't need to know it. We just need to know every other detail of the job you ran. And there is occasionally Ask Me Anythings, which might be relevant in some cases. Yes.
Sorry, just one quick point. If you are contacting the help desk, put interns,
Yes.
intern in your message title, so we know it's coming from you as an intern.
Yeah, so there's different ways of getting assistance. We even have Ask Me Anythings that occasionally show up. Usually they're themed. So maybe while you're an intern, there'll be one that's very appropriate for the type of work you're doing. You can join in and have a conversation. And that's the end of the second half of the training. I hope that was informative of the vault. And if there are any last questions, please feel free to ask.
Yeah, thank you, Pascal. Thank you, Christian and Alexis and Basha for answering questions and everyone contributing. Thank you all for your time and attending. Are there any other questions? I think it's a great idea to have a Ask Me Anything session sometime and to get the same group of people in here in case there are any questions coming out once you jump into your projects and jump into your code.
A reminder as well, remember the reservation is still up for a couple of days, so feel free to play. And if you have questions about some of the slides related to the repository that we provide in the code base, feel free to, I mean, you can ask the mentors as well. I've provided them, at least Edric, and hopefully shared the links. So they are familiar with the code base and also some of the parallelism that is explored there.
All right, again, thank you. I will stop the recording. If there are any other questions,